Have you ever laid in bed at night and wondered, how big is this universe really? Why does it exist at all? Where does it end? Or does it? And what strange truths are out there waiting for us to notice? You're not alone in asking. The universe is vast, ancient, and filled with mysteries that can quietly blow your mind, even as you're falling asleep. In the next 3 hours, we're going to explore it together. Not with loud facts or fast talk, but slowly, gently, one incredible science truth at a time, designed to help your body relax and your imagination drift beyond the stars. So before we begin, tell us, where are you listening from tonight? What time is it for you right now? Drop it in the comments below. And if you enjoy calm, thoughtful science that helps you sleep, subscribe and help us reach subscribers. Now, take a deep breath, let your eyes grow heavy, and let's begin with one of the strangest facts about the cosmos. Chapter 1. The universe has no center and no edge. It's one of the strangest facts in all of cosmology, something that challenges our everyday logic and stretches the imagination far beyond what our senses can grasp. The universe has no center, and it has no edge. To most of us, that doesn't make sense at first. We live in a world defined by boundaries. Rooms have walls, countries have borders, planets have surfaces. Everything begins somewhere and ends somewhere else. But space, real cosmic space, doesn't work like that. From the moment the Big Bang occurred, the universe has been expanding. But it didn't explode like a firework in the night sky. It wasn't a blast from a single location into pre-existing space. Instead, space itself began to stretch. Not just outward, but everywhere at once. Every point, every direction, all expanding uniformly. This is incredibly hard to picture because our brains evolved to think in three-dimensional surroundings. We imagine explosions moving through air. We imagine balls thrown across fields, cars driving on roads, waves crashing on shorelines. But the Big Bang wasn't an explosion in space. It was the expansion of space itself. Think of it like this. Imagine a balloon and picture small dots drawn all over its surface. As the balloon inflates, the dots move farther apart from one another, not because they're moving on their own, but because the surface they sit on is stretching. That surface represents space. Now imagine that instead of a two-dimensional balloon, it's a three-dimensional space that's growing, stretching in every direction. That's what's happening to our universe. And here's the wild part. If you lived on one of those dots, say a distant galaxy, you would see every other dot moving away from you. It would look like you were at the center. But someone living on another dot would see the same thing. That's because expansion is happening everywhere, not from any single point. It creates the illusion of being at the center, no matter where you are. This is why astronomers say the universe is isotropic and homogeneous on large scale. That means it looks roughly the same in every direction, and every part of it is statistically similar to every other part. You can point your telescope north, south, east, or west. Zoom into deep space and see galaxies spreading out the same way in every direction. There's no central point from which it all began, and no outer wall we're racing toward. There's just more space, more time, more unfolding. And what about the edge? Surely if something is expanding, it must be expanding into something, right? Surprisingly, no. That's another way in which cosmic reality defies intuition. The universe isn't expanding into empty space beyond its edges. Instead, space itself is growing, and the expansion defines the limits of what can be observed, not because there's a barrier, but because of the limits of light, time, and distance. We talk about the observable universe, which is about 93 billion light-years across. That means, based on how long light has had to travel since the Big Bang, we can see objects that are roughly that far away. But that's not the size of the entire universe. That's just how far our cosmic horizon stretches. What lies beyond that? Maybe more galaxies, maybe infinite space, maybe a cosmic boundary we can't yet comprehend. Or maybe nothing at all, at least not in any form we're used to describing. Some physicists believe the universe could be infinite, endless in all directions. Others think it may curve back in on itself like the surface of a sphere, meaning if you could travel in a straight line long enough, you'd eventually return to where you started, even though you never hit a wall or turned around. This would be a finite but unbounded universe. Like the balloon analogy again, there's only so much surface, but you can keep walking forever without falling off the edge. There is no edge. There is only space, wrapped in on itself in a higher dimensional way we can barely grasp. The fact that we even have these tools of understanding is remarkable. Thanks to Einstein's theory of general relativity, we know that space isn't a passive backdrop. It bends, it curves, it moves, it stretches. It can be warped by mass, bent by gravity, and reshaped by the passage of time. Our instruments, satellites, telescopes, space probes have confirmed these predictions with incredible precision. We've seen the stretching of light as galaxies drift away. We've measured the faint microwave background radiation left over from the Big Bang, still echoing across the universe like a soft, ancient hum. And we've mapped how that energy spreads evenly across the sky, reinforcing the idea that there's no single center we can point to. And yet, despite all this knowledge, there's still mystery. Because even with all we've discovered, the deepest truths of the universe remain just beyond reach. If the universe has no center and no edge, what does that mean for us? For our place in the cosmos? It means that Earth is not the middle of creation. It means our sun is not at the center of a vast dome. It means every point in space is equally valid, equally meaningful, equally a part of the great unfolding story of existence. It's humbling, but also deeply freeing, because it means we're not outliers. We are the universe, looking back at itself. We're not in some random corner. We are wherever we are, and that's enough. So what does it feel like to be inside a universe with no center and no edge? It feels like stillness and motion at the same time. It feels like drifting gently on a current you didn't know was there. It feels like looking out into the stars and knowing that the space between them is growing quietly, slowly, invisibly every second of every day. Galaxies move apart, not because they're flying through space, but because the space between them stretches. Over billions of years, this stretching adds up. Some galaxies are now so far away from us, and moving so quickly that their light will never reach us. Not because they're faster than light, but because the space between us is expanding faster than light can catch up. And still, from our tiny home on Earth, we watch, we learn, we wonder. We build telescopes that can look 13 billion years into the past. We study the echoes of creation. We model the expansion. We debate the geometry. And still, we cannot find a center. We cannot find an edge. Only the infinite possibility of more space, more time, more to learn. So the next time someone asks, where is the center of the universe? You can smile and say, everywhere. And if they ask where it ends, you can whisper, it doesn't. Let that idea stay with you. Let it wrap around your thoughts like a soft blanket. Because the universe doesn't just defy boundaries. It invites you to let go of them. You are floating in a sea of expanding space. Not lost, just part of something immeasurable. Something without center. Something without end. And in that stillness, you can sleep. Chapter 2. You are made of star stuff. When most people look up at the night sky, they see stars as distant glowing dots, cold, unreachable, scattered far beyond anything we can ever truly touch. They might admire the view for a moment, maybe feel small, and then carry on with their day, believing that the stars belong to another world, something separate from life on Earth. But science has revealed something very different. Something surprising, something humbling. The stars are not just out there. They are in us. Quite literally, every part of your body is made of atoms. Carbon, oxygen, nitrogen, calcium, iron, and dozens more. These are not just random materials that happen to come together. They have an origin. And that origin is written into the history of the cosmos itself. The carbon that makes up your skin, the iron that moves through your bloodstream, the oxygen you breathe, even the tiny traces of heavier elements in your bones and organs, all of them were formed inside stars that lived and died long before our solar system ever existed. In the early universe, just after the Big Bang, there were no heavy elements. There was only hydrogen, a bit of helium, and the faintest traces of lithium. Everything else, everything that makes life possible, had to be forged later on in the hearts of stars. Inside those stars, nuclear fusion gradually combined lighter atoms into heavier ones. Hydrogen atoms fused to become helium. Helium atoms fused to become carbon and oxygen. Eventually, through more complex reactions under intense pressure and heat, stars created even heavier elements like silicon and iron. But these elements didn't stay locked inside those stars. They couldn't. When a star runs out of fuel, when there's nothing left to fuse, it becomes unstable. The delicate balance between gravity pulling inward and heat pushing outward collapses, and in massive stars, that collapse leads to a catastrophic explosion, a supernova. In that brief and violent moment, elements are flung across the galaxy, scattering like seeds in every direction. It is during these explosive events that the heaviest elements, those beyond iron, are created in even more extreme reactions. These stellar remnants drift through space, becoming part of vast clouds of gas and dust. Over time, gravity begins to act on those clouds again, pulling matter into clumps, causing it to swirl, to heat up, and eventually to ignite new stars. Around those new stars, more matter gathers into planets, moons and asteroids, and on at least one of those planets, our Earth, some of that matter formed oceans, atmosphere, continents, and over time life. That means the material that formed our bodies did not begin here. The atoms in your hands, your heart, your brain, all originated in the interior of stars that exploded billions of years ago. Those stars may have burned in corners of the galaxy we'll never locate, and their light may have faded long before Earth was even formed. But what they left behind became part of the building blocks of you. This idea that we are made of star stuff is not meant to be poetic. It is a precise, observable fact, grounded in chemistry and astrophysics. When scientists study the elemental composition of the human body, they find the very same elements forged in the life cycles of stars. And when they analyze the material ejected by supernovae or the contents of distant nebulae, they find the raw ingredients of life. In fact, if you were to reduce a human body down to its most common elements, the list would look remarkably familiar to an astronomer. Oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus, sulfur, sodium, chlorine, magnesium and iron. These are not just parts of biology, they are also key components of planetary dust, asteroid cores and stellar remnants. We don't just come from the Earth, we come from the stars. It's a strange thing to think about that the air we breathe, the water we drink, and even the thoughts in our head are connected by origin to ancient cosmic events. But the evidence is solid. There is nothing in your body that did not come from something old. Every cell is made of atoms that have existed for billions of years. Those atoms have passed through stars, through clouds of space dust, through volcanic eruptions and chemical reactions, through plants, animals, oceans and air. They have been part of many things before they were part of you, and eventually they will become part of something else. Just as atoms once belonged to stars and now belong to your body, they will one day return to the Earth, or to the atmosphere, or perhaps to something not yet imagined. Matter is not destroyed. It changes form, it cycles. The universe reuses everything. In this way, we are not isolated observers of the cosmos, we are direct participants. When you look at the stars, you are looking at your history, not in a symbolic sense, but in a physical one. The connection between you and the universe is not a feeling, it is a fact. You are the product of cosmic processes, as real and measurable as gravity or motion. Even now, inside your body, nuclear reactions are taking place on a much smaller scale. Your cells are powered by energy that ultimately comes from the sun, a star. Plants absorb light from the sun and convert it into chemical energy through photosynthesis. You eat those plants, or you eat animals that ate those plants. Either way, the energy that fuels your body originated in a star. Every step of life is a continuation of a chain that began in nuclear fusion. Your thoughts, your movements, your dreams, all of them depend on energy released by atoms formed in stars. Every idea that passes through your mind is carried by electrical impulses in your brain, and those impulses depend on the behavior of electrons, which move through pathways shaped by atoms older than Earth itself. Even your ability to wonder about your own existence comes from the elements those ancient stars created. Without carbon, you would have no cells. Without oxygen, no respiration. Without calcium, no bones. Without iron, your blood could not carry oxygen. Each function in your body depends on atoms that were forged in cosmic heat, scattered in stellar winds, and eventually gathered into the planets that now holds you. So when people say you are made of star stuff, they are not exaggerating. They are stating a truth more profound than most people realize. You are not just connected to the universe, you are a direct extension of it. Your life is a continuation of processes that began in galaxies far older than Earth, shaped by forces that existed long before humans learned to name them. And because of that, there is a kind of quiet symmetry in everything you do. Every breath you take, every step you make, every word you speak, it all reflects the movement of atoms that once burned at the heart of a star. The hydrogen in your body has likely never been inside a star, but the rest have. The carbon, nitrogen, oxygen and iron, they carry the legacy of the cosmos. They are the remains of stellar generations, now forming thoughts, emotions and memories in a body that walks beneath the very sky it came from. In that sense, you are both ancient and new. The material that makes you is billions of years old, but the form you are in right now, this person, this mind, this presence, is something that has never existed before. You are a temporary arrangement of atoms, held together for a while, shaped by biology, animated by energy, and capable of asking questions about the stars that gave you form. And those stars, many are still out there, burning silent. Others have faded, collapsed, or become something else entirely. But their influence continues, their atoms are here, all around you, within you, and always will be. As we move forward, keep that in mind. Every fact we explore, every mystery we touch, is part of a greater whole. And you, by listening, by wondering, by learning, are part of that too. Now let's go deeper. Chapter 3: Time moves slower. Near gravity. Time is something we usually take for granted. We follow the ticking of clocks, the rising and setting of the sun, the rhythms of sleep and waking, and the patterns of our calendars. Time seems fixed, regular, constant. We live our days assuming it moves the same for everyone, everywhere, all the time. But the truth, confirmed by decades of physics, is far stranger. Time does not tick evenly throughout the universe. In fact, time itself can stretch, bend and slow down depending on where you are and what surrounds you. This effect is not just theoretical, it is real. It has been measured, tested and built into the very technology that powers our modern lives. Your GPS wouldn't work properly if we didn't account for it. And it all comes down to gravity. Gravity doesn't just pull on objects, It doesn't only make things fall or hold planets in orbit. Gravity also affects time. The stronger the gravitational field you are in, the slower time moves for you compared to someone farther away from that field. That might sound impossible at first, but it is a direct prediction of Einstein's general theory of relativity. And it has been confirmed in both small and massive ways. Imagine two people. One lives on the top floor of a tall building. The other lives on the ground floor. The person closer to the center of the Earth, the one on the ground, is in a slightly stronger gravitational field. It's not dramatic, but it's enough that time, for them, actually moves more slowly than it does for the person living higher up. The difference is tiny, just a few billionths of a second over a year, but it's measurable. This phenomenon is known as gravitational time dilation, and while it's subtle near Earth, it becomes much more dramatic in extreme conditions. Near a black hole, for example, the gravitational pull is so intense that time slows down drastically. If you were to hover near the event horizon, the point of no return, time for you would crawl compared to someone watching from a safe distance. You could spend just a few minutes near the black hole, and by the time you returned, years or even decades could have passed elsewhere. This is not science fiction. It's a real, observable consequence of how gravity warps space and time. Time is not a background constant. It is part of the fabric of the universe. And just as gravity can bend space, it can stretch and compress time. It helps to think of space and time not as separate things, but as one unified structure, what physicists call space-time. Mass and energy tell space-time how to curve, and that curvature tells objects how to move. Light, matter and time itself all follow the contours of this geometry. The more massive an object, the deeper the curve, and in that curved space, clocks run slower. This effect has even been confirmed by placing synchronized atomic clocks at different altitudes. When one is placed at the top of a mountain and another at sea level, after enough time has passed, the two clocks no longer agree. The clock lower down, closer to Earth's center, ticks more slowly. Our everyday experience doesn't notice it, but the instruments, satellites orbiting Earth, also experience time differently. Because they are farther from the planet's center and moving quickly, their clocks run faster than those on the ground. GPS satellites, for example, have to correct for both special relativity due to their high speed and general relativity due to their distance from Earth's gravity. If we didn't apply these corrections, GPS would be inaccurate by several kilometers within a day. So every time you use your phone to find directions, you are relying on Einstein's theories of time and gravity. Without them, modern navigation would simply fall apart. But beyond the technology, there's a deeper implication. Time is not universal. It is not absolute. There is no single cosmic clock ticking the same for everyone. Instead, time is personal. It depends on where you are and how fast you're moving. It depends on your relationship to gravity. Every planet, every star, every person, every object, each experiences time slightly differently, shaped by the mass and motion around them. This means that time is not a rigid backdrop to reality. It's dynamic. It flows more slowly in valleys of gravity and speeds up in emptier regions of space. And in extreme environments, this difference can grow vast. Near neutron stars, time ticks slowly. Deep in gravitational wells, time is drawn out. Far in the voids between galaxies, time flows more freely. You could say that gravity is not just the force that binds the universe together, it's the sculptor of time itself. It stretches time like a fabric pulled taut in one place and slack in another. And we, without noticing it, live our entire lives within this ever-shifting landscape. It also means that time travel, in a limited sense, is not only possible, it's already happening. Astronauts aboard the International Space Station, because they orbit Earth at high speeds and slightly lower gravity, experience time a tiny bit differently than people on the surface. After spending months in orbit, they come back just the faintest fraction of a second younger than if they had stayed on Earth. Again, it's a very small effect, but it's real. In theory, someone could take advantage of this. If you could orbit a massive black hole safely outside the event horizon and then return to Earth, you would find that much more time had passed on Earth than for you. You would have effectively traveled into the future without any fictional machine, only by riding the curve of gravity. And this isn't limited to black holes. Anywhere mass warps space, it warps time too. The deeper you go into a gravitational field, the slower your experience of time becomes. If you were to live on a massive planet with strong gravity, you would age more slowly compared to someone on a smaller planet. If you stood near the surface of a white dwarf star, the difference would be more obvious, and near a black hole, it would be dramatic. These ideas may seem distant from daily life, but they hint at something profound. They show that our understanding of time, something so central to our lives, is not complete without understanding gravity. They reveal that time is not a steady march forward, but a river that flows differently depending on where you stand in the landscape of mass and energy. The clocks we build, no matter how precise, can only measure time in relation to where they are. There is no master clock overseeing the entire universe. There is only the relative passage of time, shaped by the shape of space. And when you lie down to sleep at night, the gravity of Earth is still at work. It's pulling you gently toward its center, holding you close. And in doing so, it's also slowing your time ever so slightly, compared to the emptiness of deep space. You won't notice, but it's there. This subtle interplay between space, time, and gravity surrounds you at every moment. You are not moving through time alone. You are moving through a curved, dynamic structure that bends beneath your feet and carries time with it. Even now, as you breathe and listen and think quietly in the dark, you are part of that flow. And in the chapters to come, we will explore how that same structure carries light, carries energy, and carries the motion of galaxies themselves through an expanding and restless universe. Because time, like everything else in the cosmos, is not fixed in place. It moves with us. And it never moves quite the same way twice. Chapter 4. Light takes 8 minutes to reach us from the sun. Every morning, when sunlight filters through your window or warms your skin as you step outside, it's easy to think of it as something immediate, something present. You feel it as soon as the sun rises, you see it as soon as the clouds break, and it seems as if it arrives the moment it leaves the sun. But that sense of instant connection is an illusion. The light you are seeing, the warmth you are feeling, has traveled a long journey through space and time to reach you. In truth, it is not the sunlight of now. It is the sunlight of 8 minutes ago. The distance between the Earth and the Sun is vast, roughly 93 million miles, or about 150 million kilometers. Light, although incredibly fast, still takes time to cross that span. It moves at approximately 29,792 kilometers per second, or about At that speed, light from the Sun takes just over 8 minutes and 20 seconds to reach Earth. That means every time you look up and see the Sun, you are not seeing it as it is, but as it was over 8 minutes earlier. If for some unimaginable reason the Sun were to suddenly disappear, we wouldn't know it right away. The sky wouldn't go dark in an instant. The Earth wouldn't feel the loss of gravity immediately. For just over 8 minutes, everything would seem normal. The light would still pour down. The warmth would still remain. And only after those minutes had passed would the reality reach us. This delay is not unique to the Sun. It applies to every object in the universe. The farther away something is, the longer its light takes to arrive. When we look at the moon, we see it as it was a little over a second ago. When we look at Jupiter, we see it as it was about 30 to 50 minutes ago, depending on its position in orbit. And when we look at stars in the night sky, we're looking far deeper into the past, years, centuries, and in many cases, millennia. That's one of the most extraordinary things about astronomy. It's not just the study of space. It's the study of time. Telescopes are like time machines. The farther they see, the further back in time they reach. When you look at a galaxy a billion light years away, you are seeing it as it was a billion years ago, not as it is today. That light has spent an entire geological era traveling through space to arrive at your eyes or to be captured by your instruments. Even more remarkable is the fact that the sun's light didn't just take 8 minutes to cross space. It took hundreds of thousands of years, maybe even 1 million, to escape the sun itself. Deep in the core of the sun, where nuclear fusion takes place, photons are created through the fusion of hydrogen atoms, but they don't travel outward in a straight line. The sun's interior is incredibly dense, and photons scatter constantly. They are absorbed, re-emitted, bounced around in random directions. This process, often called the random walk, slows the progress of a single photon dramatically. It can take hundreds of thousands of years for it to reach the surface of the sun. Only after it breaks free from that chaotic interior can it begin its uninterrupted journey through space. So the light you see when you step outside in the morning carries with it a timeline that stretches back almost unimaginably far. Its story began in the sun's core, long before human civilization, before the last ice age, before even the emergence of modern Homo sapiens. That same energy, now warming your skin or feeding the plants in your garden, began its journey in the deep heart of our star. An unimaginably long time ago, it has traveled across space, uninterrupted, just to reach the Earth. And yet, for all that distance and time, light remains the fastest thing we know. It defines the cosmic speed limit. Nothing can travel faster than light in a vacuum, not even gravity. And so the time light takes to travel tells us the fundamental pace at which the universe operates. The sun's 8-minute delay is just one example. When we talk about seeing galaxies that are millions or billions of light years away, what we're really saying is that we're seeing the universe as it used to be, long before Earth even existed. This also means that space is not a stage where everything happens simultaneously. There is no universal now in the cosmos. Every object we observe is a window into its own past. When astronomers use deep space telescopes like the James Webb or the Hubble, they are literally looking back in time. Some of the galaxies they see are so far away that their light began traveling toward us more than 13 billion years ago, shortly after the universe itself began. These are not photographs of what exists today. They are snapshots of ancient history, preserved in beams of light moving steadily across the dark. Even the colors we see in sunlight carry story. The light that reaches Earth from the sun spans a wide range of wavelengths, from high-energy ultraviolet rays to lower-energy infrared. But most of the visible light we see lies in a tight band of wavelengths that just happen to correspond to what human eyes evolved to detect. These rays are scattered in the atmosphere, reflected by clouds, and absorbed by plants. They warm oceans, drive weather, and allow life to grow. All of this from energy that began its life in a nuclear reaction in the sun's core so many ages ago. That energy is constant. The sun produces an astonishing amount of it, about 86 billion megawatts every second, and yet only a tiny fraction of that energy ever reaches Earth. But it's enough. It's more than enough. That small share powers photosynthesis, fuels the water cycle, drives wind and climate, and provides almost all of the energy that life on Earth has ever known. Fossil fuels, for example, are just ancient sunlight stored in plant matter and released again after millions of years underground. In this way, the 8-minute journey of light is not just a scientific curiosity, it's a thread that connects your daily life to the vast unfolding mechanics of the solar system. Every time you feel the sun on your face, you are touching something that began its life hundreds of thousands of years ago in the heart of a star and spent 8 minutes crossing a silent void just to reach you. That connection is constant, quiet, and unbroken. It's humbling in a way to think that even something as familiar as sunlight is not immediate. It is ancient, it is traveling, it is delayed. And this delay, small as it may seem, is a constant reminder that space is big, that distance matters, that time, even in something as simple as a ray of light, is always moving forward, but never as quickly as we assume. So as you lie still now, eyes closed, listening quietly, remember that the warmth of the sun you felt this morning actually left its source before you tied your shoes, before you got out of bed, before you even opened your eye. It crossed the distance between star and planet while you made your morning coffee or walked out the door. And every sunrise, no matter how familiar, is really a glimpse into the past. Everything you see in the universe, every star, every planet, every galaxy, is reaching you not in real time but through time, delayed by distance, marked by light, delivered from moments that have already passed. As we continue our journey through the cosmos, keep that in mind. Even the simplest truths, like the warmth of the sun, carry the weight of cosmic history. Every moment is part of a longer journey, and that journey is still unfolding. Chapter 5. The moon is slowly drifting away from Earth. When you look up at the moon, especially on a clear night when its shape is full and glowing, it's easy to imagine that it has been just as it is, calm, constant, unchanging in its orbit. It seems to hold the sky in place, rising and setting with quiet reliability. But the truth is, the moon is not frozen in space. It is moving, gradually, persistently, silent. And over time, that motion is changing the relationship between the moon and the Earth in ease that most people never notice. Every year the moon moves a little farther away from us. It's not much, about 3.8 centimeters annually, roughly the rate at which your fingernails grow, but over long stretches of time, this drift adds up. It's not just an isolated shift. It's part of a complex gravitational interaction between two massive bodies, bound together by invisible forces, influencing each other in a continuous exchange of motion and energy. To understand why the moon is drifting away, we have to look more closely at the relationship between it and the Earth. Not just in terms of distance, but in terms of motion, gravity, and rotation. The Earth rotates on its axis once every 24 hours, and that spin creates the familiar rhythm of day and night. The moon, on the other hand, orbits the Earth about once every 27.3 days, always showing us the same face, because it is tidally locked, meaning its rotation and its orbit are synchronized. But this system isn't perfectly still. As the Earth spins, it creates a tidal bulge in the ocean. The moon's gravity pulls on these bulges, and in return, the bulges pull on the moon. Because the Earth rotates faster than the moon orbits, these tidal bulges are slightly ahead of the moon in its path, which creates a kind of gravitational tug that accelerates the moon in its orbit. That added energy causes the moon to slowly move farther away. At the same time, the Earth's rotation slows down very gradually, losing angular momentum as it transfers some of its energy to the moon. This process, called tidal acceleration, has been occurring for billions of years. When the moon first formed, it was much closer to the Earth, possibly only 20,000 to 30,000 kilometers away, compared to the current average of about. Back then, a day on Earth was much shorter, perhaps only 5 or 6 hours long, and the tides would have been dramatically more intense. As the moon moved outward, Earth's rotation slowed, and the length of our day gradually increased. Scientists know this not only from theoretical physics, but also from studying ancient rocks and fossils. In certain formations you can find tidal patterns preserved in sediment layers, showing the changing rhythm of Earth's days and the moon's orbit over hundreds of millions of years. These natural records, combined with precise laser measurements taken from mirrors left on the moon's surface during the Apollo missions, confirm that the moon is indeed drifting away slowly but surely. The effects of this drift aren't something we feel in our daily lives, but they do shape the long-term evolution of Earth's environment. As the moon moves away, its influence on tides becomes slightly weak. Tides are still significant and will remain so for a long time, but over geological timescales, this gradual weakening changes the dynamics of coastal ecosystems, the mixing of ocean water, and possibly even patterns of climate regulation tied to the ocean's behavior. Perhaps even more interesting is what this process implies about the distant future. If the moon continues to move away, there will eventually come a time billions of years from now when it will no longer be able to fully eclipse the sun. Right now, total solar eclipses are possible because the moon appears just the right size in the sky to completely cover the sun's disk. But as it drifts outward, its apparent size will shrink. In the far future, all eclipses will become annular, with the sun forming a bright ring around the dark moon. The era of total eclipses, beautiful and rare as they are, is temporary. That future may be distant, but it's a reminder that even the things that seem most permanent are always in motion. Nothing in the cosmos is truly fixed. The moon has been a part of Earth's story for over 4 billion years, and yet it is still moving away, inch by inch, year after year. And in the far reaches of time, it may move so far that it becomes gravitationally independent, no longer in orbit, or the dynamics may shift into a stable equilibrium where its motion halts. The idea that the moon is drifting away can feel strange at first. It's not something we notice. The night sky looks the same as it always has. The moon rises, sets, and cycles through its phases with the same quiet rhythm. But if we could speed up time, if we could watch millions of years pass in seconds, we would see the moon spiraling gently outward, Earth's spin gradually slowing, and the dance between these two celestial bodies evolving in a smooth and silent ballet. This movement is not destructive. It's part of a natural exchange. The Earth and Moon are bound by gravity, and gravity, like all fundamental forces, is not static. It allows motion, transfer, drift, and subtle change. The system isn't breaking, it's breathing. Even the act of drifting is shaped by forces deeper than most people realize. Gravity, angular momentum, and the shape of Earth's oceans all contribute to this change. And while the pace is slow, the significance is enormous. The moon affects more than just tide. It stabilizes Earth's tilt, which in turn moderates our climate. Without the moon, Earth's axial tilt might vary wildly, leading to unpredictable and extreme climate changes. The moon acts as a kind of anchor, a steadying hand in a spinning, dynamic world. So even as it drifts away, the moon continues to shape Earth's destiny. Its motion reminds us that the universe does not stand still, not even for the most familiar and comforting things. Change is always underway, even if it's too slow for human eyes to see. When you stand outside at night and look up at the moon, whether it's a thin crescent, a bright half, or a full white circle hanging in the sky, you are looking at something ancient and active, something that formed from the debris of a collision, became a quiet partner to our planet, and continues, even now, to move outward, millimeter by millimeter, year after year. And though it drifts, it doesn't leave. It remains in orbit, bound by gravity, part of the same dance it's always known. But the steps are slow, the rhythm is cosmic, and it reminds us that time is long, that motion is everywhere, and that the very structure of the sky is shaped by relationships we can barely feel, yet know to be true. As we move onward into deeper parts of space and stranger truths about the universe, remember that even something as close and familiar as the moon is not frozen. It too is part of the great unfolding, and it too carries us forward. Chapter 6. Black holes aren't just destroyers, they preserve information. When most people think of black holes, they imagine them as bottomless pits, dark, destructive objects that swallow everything around them. The idea is dramatic and often intimidating, a place in space where gravity is so strong that nothing, not even light, can escape. And while that basic idea is true to a point, the reality of black holes is far more complex, far more mysterious, and much more fascinating than most people realize. Black holes are not holes in the traditional sense. They are not empty spaces, And they are not portals, they are regions of space where matter has been compressed to such an extreme density that gravity becomes overwhelming. When enough mass is packed into a small enough volume, it creates a gravitational field so strong that beyond a certain boundary, called the event horizon, nothing can get out. No light, no sound, no information. But black holes aren't just destroyers, they are also record keepers. And what they appear to be recording is one of the most fundamental quantities in all of physics: information. In physics, information doesn't just mean data or knowledge in the human sense. It means the arrangement of particles, the state of matter, the specific configuration of energy, position, momentum, and charge that makes up any object or system. According to our best understanding of the universe, this information is never truly lost. It might change form, but it cannot simply vanish. That principle is central to quantum mechanics, one of the most successful theories in science. So this creates a puzzle. If black holes destroy everything that falls into them, including the identity of those objects, then where does the information go? If a book falls into a black hole, not only is the paper and ink lost, but also the precise arrangement of atoms that made it what it was. If a star collapses into a black hole, do we lose all record of its structure, its composition, its internal activity? For a long time, this seemed to be the case. According to classical general relativity, all information about the matter that falls into a black hole is lost behind the event horizon. The black hole could be described by only a few simple properties: mass, charge, and spin. This led to the phrase, "black holes have no hair," meaning that they show no detailed features of what created them. But this idea didn't sit well with many physicists, especially those working in quantum theory. One of them was Stephen Hawking. In the 1970s, he made a revolutionary discovery. He showed that black holes aren't entirely black. Thanks to quantum effects near the event horizon, black holes emit radiation now called Hawking radiation. This radiation causes black holes to slowly lose mass and eventually evaporate over incredibly long timescales. But this only deepened the mystery. If black holes eventually disappear and the radiation they emit is purely random, then the information about what fell in seems to be lost forever. This would violate the fundamental principle of quantum information conservation. Physicists called it the black hole information paradox, and this paradox sparked decades of debate. Over time, more detailed theories emerged. Some suggested that information might be encoded in the Hawking radiation itself, just in a way we don't yet understand. Others proposed that the information might be stored at the event horizon in a kind of holographic form, a theory supported by what's now known as the holographic principle. The holographic principle suggests that all the information contained within a volume of space can be described by data encoded on the boundary of that space. In the case of black holes, that boundary is the event horizon. It may be that the information about everything that falls in gets somehow smeared across that surface, encoded in subtle fluctuations too small to detect. If this is true, then black holes are not destroying information. They are preserving it in a form we just don't fully understand. Recent theoretical work, including ideas from string theory and quantum gravity, has added support to the idea that information is not lost in black holes. In fact, many physicists now believe that a complete theory of quantum gravity, one that successfully merges general relativity with quantum mechanics, will eventually resolve the paradox and show exactly how black holes retain this information. So rather than being the ultimate destroyers, black holes may turn out to be deeply structured, highly ordered systems, strange archives of cosmic history. They might contain within them the record of every atom, every photon, every field that has ever crossed their boundary. This concept challenges our understanding of reality. If black holes preserve information, even after evaporation, then there is no true erasure in the universe. Everything that has ever happened still exists in some form. No particle ever truly disappears. No process is beyond reconstruction. In principle, though far beyond our technological capabilities, If you had the exact mathematical tools and the right access to the data, you could reconstruct what went into a black hole from the information it still contained. That doesn't mean you could recover a person, or a planet, or a memory in any practical way. The reconstruction would be impossibly complex. But the idea matters, because it means that the universe plays by rules, rules that hold even in the most extreme conditions. Even now, physicists continue to explore the edges of this mystery. Some studies suggest that wormholes, hypothetical tunnels through space-time, could be related to the way information is preserved in black holes. Others have proposed that space-time itself may emerge from entangled quantum information, and that black holes offer a kind of laboratory for testing this idea. Despite the many unknowns, the trend is clear. Black holes are not blank. They are not purely destructive. They are not violations of physics. They are, in fact, deeply lawful, perhaps more so than we can yet comprehend, and their role in the cosmos may not be to end things, but to encode them in new forms. That's why many physicists now see black holes not just as destinations, but as bridges, not just as deaths, but as transformations. A star becomes a singularity. A singularity becomes an object with entropy, temperature, and information, and that object continues to influence its surroundings, not just with gravity, but with meaning. And even more astonishing is the idea that you yourself are connected to black holes in more than a distant way. Every atom in your body follows the same rule. The conservation of information, the laws of entropy, the structure of quantum states, all of it applies to you just as it applies to the most extreme objects in the universe. In that sense, the mystery of black holes is not just a distant curiosity. It is part of the same fabric of reality that defines you, your experiences, your memories, and your presence in the world. You live in a universe where nothing is wasted, where even in destruction, there is structure, where even at the edge of collapse, there is order. So when you think of black holes, don't picture emptiness, picture complexity, picture density not just of mass, but of knowledge. Picture a region of space where the past is stored, where the future is shaped, and where the rules of the universe continue to hold firm, even in darkness. As we move forward in our journey, remember that the universe often hides its most surprising truths inside the places we fear the most. And those truths are still unfolding. Chapter 7. Every atom in your body has existed for billions of years. When you look at yourself in the mirror, you might see the signs of a recent life. Hair that needs cutting, skin that reacts to the weather, a body that seems to change slowly over time. But what you're seeing is only the current arrangement. The deeper truth, quiet, invisible, constant, is that every atom in your body has been here far longer than you have. Atoms are the basic units of matter, and they are not created new inside your body. They are not freshly generated each day. They are inherited, reused, recycled from older forms. Your body is a temporary combination of ancient ingredients drawn from a reservoir of matter that has existed since the beginning of time. The hydrogen atoms in your body are the oldest. They were formed just a few minutes after the Big Bang over 13.8 billion years ago, when the universe was still in its infancy. In that early era, the cosmos was a hot, dense plasma rapidly expanding and cooling. As it cooled, protons and neutrons began to combine to form the nuclei of the first atoms. Hydrogen, helium, and trace amounts of lithium emerged from this process, forming the first building blocks of all matter. Some of that hydrogen is still in you now. It makes up part of your water. It exists in your organic molecules. It flows through your bloodstream and shapes your cells. That hydrogen is older than the Earth, older than the stars, older than time as you understand it. The other elements in your body, carbon, nitrogen, oxygen, phosphorus, sulfur, calcium, and more, have different origins. They were forged inside stars through nuclear fusion. As stars aged and burned through their fuel, they created heavier and more complex atoms in their cores. When those stars reached the end of their lives, Some gently shed their outer layers, and others exploded in spectacular supernovae, dispersing their contents into space. Those elements became part of gas clouds. Those clouds condensed under gravity, planets formed. And from those planets, life eventually emerged. You are composed of these recycled materials. The atoms in your bones and brain and blood were once part of other stars, other systems, other structure. They have been part of comets, rocks, oceans, trees, air, and even the bodies of countless living things before you. Every breath you take contains molecules that have circulated through the lungs of others, humans, animals, plants, and beyond. The oxygen you inhale today may have been inside a leaf a week ago, or a glacier a century ago, or an ancient organism millions of years in the past. The carbon in your cells could have been part of volcanic gas, limestone, or the body of a trilobite. The calcium in your bones may have passed through ocean sediments, mollusk shells, or the skeletons of marine reptiles long before the first humans appeared. And the iron in your blood, that essential element that carries oxygen through your veins, was born in the final moments of massive stars, released in stellar death, scattered across the galaxy, eventually becoming part of the raw material that formed the Earth itself. You are not just alive now, you are made of things that have always existed. What changes is not the atoms themselves, but their arrangement. The way they are combined, the way they interact, the structures they form. Life is not made from new matter, but from the reorganization of matter that already exists. Your body is a temporary structure. Your atoms were elsewhere before you were born, and they will be elsewhere long after you're gone. Even while you are alive, your atoms are in motion. They are exchanged constantly with the environment. When you eat, you take in atoms. When you breathe, you trade gases with the atmosphere. When you shed skin, exhale, or lose hair, you return atoms to the world around you. There is a constant flow, matter moving in and out, being reshaped, reused, redistributed. You are part of an enormous cycle that spans the entire planet, and more broadly, the entire galaxy. The molecules in your body, though incredibly complex, are just combinations of simpler parts. Proteins, lipids, carbohydrates, and nucleic acids are all made from familiar atoms arranged in specific ways. But the atoms themselves have no memory of the forms they've taken. They do not know they are part of a person now. They simply follow the rules of chemistry and physics, joining, breaking, forming new bonds, and continuing the cycle. This is not just philosophy, it is supported by real science. We know the age of atoms by observing cosmic background radiation, by measuring isotopes in ancient rock layers, and by tracing the fusion processes in stars. We understand the cycles of carbon and nitrogen, how they move through the biosphere, the oceans, the crust, and the sky. We know how stars form elements, how those elements are carried across light years, and how they come together to form new systems like our own. Even radioactive elements, those that decay over time, tell stories about the age of matter. Their decay rates are used to date rocks, fossils, and even the Earth itself, and yet the particles they release are often absorbed again into new atoms, starting new paths in new bodies. Energy is conserved, mass is conserved, matter is not erased, it is transformed. This means that your body is not a closed system, it is a process, one that began long before you were born and that will continue long after. The identity you experience, the person you are, is built on a framework of particles that have traveled unimaginable distances and passed through countless forms. You are not built from the present moment. You are built from everything that came before, and that perspective can be grounding. It can help you understand your place in the universe. It can remind you that even in the most mundane aspects of life, eating, sleeping, breathing, you are engaging in something ancient, something. You are made of the same matter that shaped stars and planets, oceans and mountains, forests and creatures, that no longer exist. You are not separate from nature. You are a continuation of it. The water in your body was likely part of the ocean billions of years ago. The salt on your skin was formed in geological processes tied to ancient seas. The air you breathe has passed through the lungs of animals that lived before history began. Nothing about your material form is new. It is only newly assembled. And when your life comes to an end, that matter will return to the earth. It will be taken up by plants, by microbes, by the soil. It will continue to move, continue to change, continue to take part in the unfolding story of the cosmos. This knowledge is not meant to make you feel small. It's meant to show you that you are connected, that you are part of something far larger than yourself, that you carry with you the oldest atoms in the universe, that you are not just passing through the universe is passing through. As we move into the next chapter, that idea will continue to echo, because the emptiness of space, the silence of the vacuum, and the gaps between galaxies are not truly empty. They are filled with hidden movement, subtle energy, and ancient particles, just like the ones in you. Chapter 8. Space isn't empty. It's filled with quantum fluctuations. When we talk about space, most people imagine a vacuum, an endless, silent void where nothing exists. Between stars, between galaxies, even between atoms, the common assumption is that space is simply emptiness. A background, a neutral stage on which real things happen. But that idea, while intuitive, is not accurate. According to the best understanding we have of physics, especially quantum physics, space is not empty. Not even close. It is filled with something strange, invisible, and always active. This hidden activity is known as quantum fluctuation, and it reveals a universe far more alive and dynamic than it appears. At the human scale, emptiness seems simple. If you remove all the air from a container, you've created a vacuum. It feels like you've removed everything. But at the quantum scale, the level of the tiniest particles and the deepest foundations of matter, emptiness doesn't mean nothing. It means uncertainty, restlessness, possibility. Quantum theory tells us that even when all particles are removed from a region of space, the energy field that underlies everything, the quantum field, still exists. And that field is never completely still. It seethes with activity. Pairs of particles and antiparticles constantly appear and disappear, popping in and out of existence in timescales too short to observe directly. These are not particles in the way we usually imagine. They are brief, flickering disturbances, ripples in a field that obey the strange rules of quantum mechanics. This process doesn't violate any laws. In fact, it is predicted by the uncertainty principle. That principle, one of the cornerstones of quantum mechanics, says that you cannot know both the exact energy and the exact time of a system with perfect precision. As a result, for very short periods of time, the vacuum can borrow energy and form these virtual particles as long as they disappear quickly enough to return the energy. This is not a loophole. It is how nature behaves. These fluctuations are not just theoretical guesses. They have measurable consequences. For example, in what's known as the Casimir effect, two metal plates placed very close together in a vacuum will actually feel a force pulling them toward each other, not because of static electricity or air pressure, but because of the quantum energy in the space between them. The presence of the plates alters the vacuum energy, creating a measurable physical effect that can only be explained by accepting that empty space is not truly empty. Quantum fluctuations also help explain phenomena in cosmology. In the early universe, during a period called inflation, tiny quantum variations in energy density were stretched by rapid expansion, becoming the seeds for all the structure we see today. Galaxies, stars, clusters. These began as microscopic irregularities in the vacuum, amplified by gravity over billions of years. Without quantum fluctuations, there would have been no patterns to grow from. the universe would be smooth, featureless, and lifeless. This also ties into the concept of zero-point energy, the lowest possible energy that a quantum mechanical system can have, even when it seems at rest. Every field has a zero-point energy, and even when you remove all particles, that background energy remains. It cannot be taken away. It is a built-in feature of space itself. And then there's the role quantum fluctuations may play in black holes, in Hawking radiation, and even in the expansion of the universe itself. Some theories suggest that the mysterious dark energy, the force causing the acceleration of cosmic expansion, might be connected to the energy of empty space. Though that idea is still debated, it highlights how powerful the vacuum really is. Even in a cubic centimeter of seemingly empty space, quantum theory predicts that there is an enormous amount of energy, more than we observe in total mass and energy around us. The discrepancy between this prediction and what we actually measure is one of the great mysteries in physics. It tells us we're missing something profound about how vacuum energy works, or how gravity interacts with quantum fields, or both. So the space between stars is not a blank void. It is a churning field of invisible motion. It is filled with fluctuations, with potential, with energy that may never become visible, but that influences everything from particle interactions to the evolution of the cosmos. And this activity is not localized to distant corners of the universe. It is all around you. The space in this room, the space between your hands, even the space between the particles in your body, all of it contains this same quantum restlessness. Your atoms are surrounded and shaped by a vacuum that isn't silent at all but active and alive, humming with possibility on scales too small to sense directly. This understanding reframes the way we think about emptiness. Emptiness is not the absence of existence. It is a deeper, more subtle layer of structure, a kind of invisible canvas that still contains the brushstrokes of the universe. The vacuum is not a nothing, it is a something, and it can produce real forces, real particles, real events. It also suggests that everything we experience, light, matter, force, arises not from solid, tangible building blocks, but from fields and fluctuation. At the base of reality, it may not be particles that form the universe, but fields vibrating with energy, guided by uncertainty and shaped by probability. What we see as solid is just a specific pattern formed from a field that never stops fluctuating. This view is difficult to reconcile with everyday experience, but it is supported by experiment after experiment. Quantum field theory, which incorporates these ideas, is the most successful framework ever created in physics. It predicts particle behavior with astonishing precision. It explains why electrons behave the way they do, why atoms form, why forces act as they do, and all of it rests on the foundation that space is never truly still. So the next time you look into the sky and imagine the space between stars, or consider the gaps between planets, or the darkness between galaxies, try not to picture nothingness. Try instead to imagine an ocean of activity, small, unpredictable, but persistent. Imagine fluctuations that shape the behavior of everything else. Imagine that beneath the silence is motion, beneath the stillness is structure. Because the more we learn about space, the more we realize that what we once called empty is actually full of energy, full of rule, full of the invisible dynamics that keep the universe alive. And in the chapters ahead, we'll continue exploring the invisible forces that move silently beneath what we think of as reality. Chapter 9. We've only seen about 5% of the universe. For all the satellites we've launched, for all the telescopes we've built, for all the particles we've measured, and the galaxies we recatalogued, what we have discovered amounts to only a small fraction of what the universe actually contains. Most people assume that with our growing knowledge of space, of stars, planets, clusters, and cosmic history, we must already understand a significant portion of the cosmos. But the reality is very different. The matter that we can see, the planets, the stars, the dust clouds, the comets, the oceans, the bodies of people and animals, the materials that form everything we interact with, all of that, added together, makes up only about 5% of the total energy and matter content of the universe. The rest, 95%, is invisible. And not just invisible in the way distant objects are, it's invisible in principle. It doesn't emit light, doesn't reflect it, doesn't absorb it in ways we can observe directly. And yet we know it's there. This unseen majority is divided into two great mysteries: dark matter and dark energy. Dark matter makes up about 27% of the universe. It doesn't shine, it doesn't glow, and it doesn't interact with regular matter in any way we can touch or see, except through gravity. We know dark matter exists because galaxies don't behave the way they should if only visible matter were present. When we observe galaxies rotating, the stars on the outer edges are moving far too fast to be held in place by the gravity of the visible matter alone. Something else, something massive and invisible, is exerting additional gravitational pull, holding those galaxies together. Without it, the stars would simply fly apart. This invisible mass cannot be explained by gas, or dust, or undiscovered planets. Its gravitational fingerprints are too consistent across too many systems. Dark matter also shapes the large-scale structure of the universe. It forms vast filaments and halos that guide the formation of galaxies and clusters. It bends the path of light traveling through space, creating a phenomenon known as gravitational lensing, where the light from distant objects is warped and magnified by the mass it passes through. And yet, despite knowing all of this, we still don't know what dark matter actually is. It could be made of particles that interact only weakly with normal matter, particles that pass through you, the Earth, and everything else without a trace. Physicists have proposed many candidates: WIMPs, axions, sterile neutrinos. None have yet been confirmed. Then there's dark energy, which is even more mysterious. Discovered through observations of distant supernovae in the late 1990s, dark energy appears to be driving the accelerated expansion of the universe. That discovery was unexpected. Scientists had assumed that the expansion of the universe would slow down over time due to the gravitational attraction of all the matter within it. Instead, they found the opposite. Not only is the universe expanding, but that expansion is speeding up. To explain this acceleration, something must be pushing galaxies apart. That something has been called dark energy, and it accounts for about 68% of the total energy content of the universe. Unlike dark matter, which pulls things together through gravity, dark energy pushes them apart. It acts like a kind of negative pressure built into the fabric of space itself. The more space expands, the more of this energy seems to emerge, and the result is a universe that not only continues to grow, but grows faster and faster with time. We don't know what dark energy is made of. It could be a property of empty space. It could be related to vacuum energy or quantum field, or it could be evidence of a flaw in our current understanding of gravity. What's clear is that without it, our observations make no sense. The accelerated expansion would be unexplained. The structure of the universe would be wrong. And so even if we cannot see it, dark energy must exist. So when you look at the night sky and imagine that you're seeing the full universe, you're actually seeing only a sliver of what's out there. All the stars you can count, all the galaxies you can detect, all the cosmic background radiation you can map, that is just the visible fraction, a tiny 5%. The rest remains hidden. And that 5% is still incredibly vast. It contains trillions of galaxies, each with billions of stars. It contains black holes, pulsars, supernovae, quasars, and nebulae. It contains the ingredients for life, the remnants of stellar death, and the building blocks of planets. It contains you. Yet all of it, everything you've ever touched or seen or heard about, fits into that narrow portion of reality. The overwhelming majority of the universe is something we can't see, can't touch, and don't fully understand. But its effects are everywhere. This realization is not just humbling, it is powerful. It tells us that the universe is far richer than appearances suggest. That mystery is not a temporary problem to be solved, but a fundamental part of existence. The unknown is not a gap in our knowledge. It is the landscape we live in. And even now, scientists are building instruments to detect the subtle interactions of dark matter, to measure the expansion of the cosmos more precisely, to test theories about the underlying forces that shape the vacuum. Every new observation adds a piece to the puzzle, but the full picture remains elusive. Some have wondered whether the missing 95% might one day be fully explained. Others believe that it represents the limit of what we can observe, not necessarily the limit of what exists. It may be that we will always live within this imbalance, knowing some things with clarity, and sensing others only by the way they bend the visible world around them. But that doesn't make the search any less meaningful. In fact, it makes every discovery more significant. Every galaxy catalogued, every particle tracked, every signal from deep space carries with it not only knowledge, but contrast, shining brighter because of the darkness that surrounds it. So when you think of the universe, try not to picture it as a finished map. Try to imagine it more like a vast library, most of whose books are still sealed. The few pages we've opened are fascinating, full of meaning and detail, but the majority remains unread, waiting beyond the reach of our current senses, yet undeniably. And as we move further into that mystery, we'll continue to explore what little we can see, and how even that tiny portion holds clues to the whole. Chapter 10. The speed of light is the ultimate speed limit. In our daily lives, speed feels like something we can always improve. We move faster, build faster machines, find quicker ways to get from one place to another. Technology has increased the pace of life, from vehicles to data, to the very thoughts that flash across screens. But beneath all that movement, there's a limit, a boundary written into the very fabric of reality. And that boundary is the speed of light. In the vacuum of space, light travels at a constant, unchanging speed, 399,792,458 per second. That's about 300,000 kilometers per second, or roughly 136,000 miles per second. It's incredibly fast, fast enough to circle the Earth more than 7 times in just 1 second. But more than just being quick, light's speed is absolute. It's not just a measure of how fast something goes, it's a cosmic constraint, a universal rule that no object with mass can break. This rule comes from Einstein's theory of special relativity, which showed that the speed of light isn't just a property of light, it's a fundamental feature of space-time itself. All observers, no matter where they are or how fast they're moving, will measure the speed of light to be the same. That constancy leads to all sorts of strange and beautiful consequences. One of those consequences is that nothing with mass can ever reach the speed of light. As something speeds up and gets closer to that limit, its mass effectively increases. It becomes harder to accelerate. It takes more and more energy. To actually reach light speed, an infinite amount of energy would be required. That's not just difficult, it's impossible according to the laws of physics as we understand them. Light speed is not a goal, it's a wall. Particles that have no mass, like photons, the particles of light, can travel at light speed. They don't experience time the way we do. For a photon, in a certain sense, the entire journey from one point to another happens instantly. But for anything with mass, electrons, atoms, planets, people, light speed remains forever out of reach. And yet, this limit doesn't slow us down in the ways you might expect. It gives the universe structure. It defines how causality works, what can influence what and when. It places a boundary on how fast information can travel, how quickly signals can be sent, how events can unfold. In this way, the speed of light is not an obstacle. It is a framework that makes consistent experience possible. Even in communication, we see this limit at work. When we send signals to spacecraft exploring the outer planets, we wait for light to travel back and forth. A message sent to Mars, depending on the position of the planets, might take anywhere from 4 to 20 minutes to arrive. Then we wait the same amount of time for a reply. The delay isn't technological, it's physical. Even at the speed of light, space is big. And the farther out we go, the more this delay becomes pronounced. A signal sent to the Voyager spacecraft, now traveling beyond the solar system, takes over 22 hours to reach it. Any command we send is a day-long round trip. If you were somehow able to communicate with a distant star system, say 10 light-years away, you would have to wait 10 years for your message to arrive, and another 10 years for the reply to come back. This isn't because of interference or signal degradation. It's because light, for all its speed, still takes time to cross distance. Space is vast, and time is required. The farther we look into space, the farther we look into the past. The delay becomes a window. The stars we see are not showing their current state. They are showing history. Ancient light, still in motion, and that has implications beyond communication. It shapes how we think about space travel. The dream of faster-than-light travel is one that has captured human imagination for generations. In science fiction, spaceships routinely warp, jump, or bend space to travel incredible distances instantly. But in real physics, those methods remain speculative. There are no proven ways to exceed the speed of light, and everything we currently understand suggests that doing so would violate causality, causing effects to happen before causes, breaking the logical order of time. Some theoretical ideas, like wormholes or warp drives, have been proposed as ways to bypass this limit, not by going faster through space, but by bending space itself. A wormhole could connect two distant points in space-time, allowing near instantaneous travel between them, much like folding a sheet of paper to bring two ends together. A warp drive might compress space in front of a ship and expand it behind, moving the space around the ship rather than the ship through space. But these ideas, while fascinating, remain untested. They require exotic forms of matter and energy we've never observed, and even if they turn out to be possible, they would require immense technological leaps far beyond our current reach. For now, we live within the boundary. Light defines the edge of what can be reached, what can be known, and how quickly we can experience change across distance. It also provides consistency. Because the speed of light is constant, it sets the scale for all of relativity, how time slows for moving observers, how space contracts, how mass and energy relate. And we've used that knowledge in practical ways. Satellites, for example, rely on light-speed signals to sync their positions and communicate with Earth. Lasers use light's properties to create incredibly precise instruments. Fiber optic cables transmit vast amounts of information using light, bouncing signals through glass across cities, continents, and oceans. All of this is governed by the simple fact that light moves fast, but not infinitely fast, and always at the same rate. Even the very definition of a meter, the standard unit of length, is based on the distance light travels in a set amount of time. Time and space are tied together through this speed, and through it, the universe keeps itself ordered, synchronized, and causally coherent. It's natural to wonder why the speed of light is what it is, why that number, and not faster or slower. So far, we don't have an answer. It appears to be one of the fundamental constants of the universe, something built into the fabric of reality. We can measure it, we can use it, but we don't yet know why it takes that specific value. What we do know is that it acts as a ceiling, a universal cap on how quickly anything can respond, change, or influence something else. It is the limit of speed, of information, of connection across distance. And because of that, it also defines how we explore the universe. We look into the sky and the light we see is a message, a delay, a reflection of what once was. It means that astronomy is not just a study of distant objects, it is a study of time, shaped and slowed by this speed limit we cannot break. As we continue, that limit will stay with us. It will guide our understanding of galaxies, of black holes, of expansion, of energy. Because no matter how far we go or how fast we move, we are still bound by the light that defines the boundary of what we can observe. Chapter 11. The universe is expanding faster than light. But that's allowed. In earlier chapters, we explored the idea that nothing can move faster than light. We learned that the speed of light is not just a measurement of velocity, but a built-in limit of the universe, a law so deeply woven into reality that even the fastest signals we can send must obey it. And yet, despite this rule, there is something in the cosmos that does move faster than light, space itself. At first, this seems like a contradiction. How can the universe expand faster than its own speed limit? How can distant galaxies move away from us faster than light and still remain within the laws of physics? To understand this, we have to separate two ideas, motion through space and the expansion of space. When we say that nothing can move faster than light, we're talking about objects traveling through space, a spaceship, a particle, or even light itself crossing a fixed distance. But when we talk about the expansion of the universe, we're not describing things moving across a background, we're describing the stretching of space itself. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, the dots move apart, not because they're traveling across the surface, but because the surface itself is expanding. The fabric they sit on is growing. That's similar to how galaxies behave in our universe. Most galaxies aren't flying through space away from us. They are being carried apart by the expansion of the space between them. This expansion was first discovered by Edwin Hubble He found that galaxies farther from us are moving away faster, and that their light is stretched into longer, redder wavelengths, a phenomenon now called cosmic redshift. The farther away a galaxy is, the faster it seems to be receding. This discovery revealed that the universe isn't static, it's dynamic. It's getting bigger over time. But as we look farther and farther away, something strange happens. At great enough distances, galaxies appear to recede from us faster than the speed of light. And that's not because they're breaking the speed limit. It's because the space between us and them is expanding so rapidly that the cumulative effect exceeds light speed. This doesn't violate relativity, because in relativity, speed limits apply to local motion, movement within space-time, not the expansion of space-time itself. There's no limit on how fast space can grow. That's why it's possible for distant regions of the universe to become unreachable, even in principle. Their light will never reach us, no matter how long we wait, because the space between us is growing faster than the light can cross it. And this effect is not just theoretical. It's observable. The cosmic microwave background, the afterglow of the Big Bang, shows that the early universe expanded rapidly during a phase called inflation, when the size of the universe doubled again and again in a fraction of a second. During that time, regions of space separated from each other at speeds far beyond the speed of light, but no matter moved faster than light, only space itself grew. Even today, this expansion continues, and thanks to dark energy, it's accelerating. Galaxies not gravitationally bound to us are moving away faster with time. The most distant ones are already receding faster than light. That means their light is no longer able to reach us. They are effectively disappearing from our observable universe. This expansion raises deep questions. What lies beyond the edge of what we can see? If some parts of the universe are forever out of reach, are they still part of the same cosmos? Is the universe finite or infinite? If it's infinite, then this expansion plays out endlessly, across a space with no boundary. If it's finite, it may wrap back on itself, or it may expand like the surface of a balloon, into a higher dimension we cannot detect. The math allows for both possibilities. What's clear is that we live in an expanding universe, and the rate of that expansion defines the limits of what we can observe and interact with. That boundary is known as the cosmic horizon, the maximum distance from which light has had time to reach us since the universe began. Every year this horizon grows, new light reaches us. But at the same time, more galaxies cross the threshold of visibility. The universe is not shrinking, but the portion available to us is slowly narrowing in what we can eventually access. The expansion stretches the distance between us and distant objects until their light is frozen, redshifted beyond detectability, and lost to the darkness forever. And that's one of the strange consequences of this cosmic law. Even though nothing moves through space faster than light, the stretching of space ensures that some parts of the universe are permanently beyond our reach. They aren't hidden because of dark, they're hidden because of distance that grows faster than any signal can travel. This concept also has practical meaning. It sets a limit not only on what we can study but on what we could ever explore. If we were to develop spacecraft capable of incredible speeds, even near the speed of light, there would still be vast regions of the universe we could never reach. They are receding too far. The moment we identify them, they're already gone from our grasp, like ships vanishing over a cosmic horizon. And yet, in the space we can observe, the expansion tells a story. It records the history of the early universe. It shows how galaxies formed and drifted. It provides clues about the balance between matter, radiation, and dark energy. It reveals how the structure of the universe, the filaments, the voids, the clusters, evolved from tiny quantum fluctuations into the massive formations we see today. And even though space expands, locally, things stay stable. Our solar system is not getting bigger. The Earth's orbit around the Sun is not stretching. Galaxies remain bound together by gravity. The expansion only dominates at the largest scales between clusters of galaxies, where gravity cannot hold everything together. There, space stretches gently but relentlessly, changing the shape of the universe over billions of years. So when you hear that the universe is expanding faster than light, understand that this doesn't break the rules. It shows how the rules are more nuanced, more layered, and more elegant than they first appear. It tells us that space is not a passive stage, but an active participant. It grows, it curves, it evolves. And because of this, we live in a universe that is always changing, a cosmos that never stands still, one in which even the distance between galaxies is not fixed, but fluid, shaped by forces that continue to unfold. As we go forward, we'll explore those forces further, from the invisible scaffolding of dark matter to the profound silence of deep intergalactic space, because the expansion continues, and it shapes everything we see. Chapter 12. Dark matter is invisible, but it shapes galaxies. When you gaze into the night sky and see the stars scattered above, it's natural to assume you're looking at the full picture of the universe. Stars shine. Galaxies glow. Nebulae stretch across space in soft, colored clouds. Telescopes collect that light, and images show us stunning scenes from deep space. But what those pictures don't show is perhaps even more important than what they reveal, because what we can see, the stars, the dust, the gas, makes up only a small part of what's really there. Galaxies, as luminous as they appear, are not held together by what we can see. In fact, if their mass were made up only of the stars and gas we detect, they should not be able to hold their shape. Their outer stars rotate far too quickly. Based on visible mass alone, those stars should fling off into space. But they don't. They stay in orbit. They stay bound, and that leads to one conclusion: something else must be holding them together. That something is called dark matter. Dark matter doesn't emit light. It doesn't reflect it, absorb it, or scatter it. It doesn't glow under infrared or ultraviolet. It passes through electromagnetic fields, without disturbance. It interacts with the rest of the universe almost exclusively through gravity, and yet it outweighs all visible matter by more than 5 to 1. Most of the matter in the universe is not made of atoms. It is something else entirely. This discovery didn't come from one single observation. It emerged slowly from layers of evidence across decades. In the 1930s, astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving much faster than expected. Based on the gravitational pull of the matter we could see, the cluster should not have been able to hold together. Something unseen had to be contributing extra gravity. Later, in the 1970s, Vera Rubin studied the rotation curves of individual galaxies. She found that stars far from the galactic center were orbiting just as fast as those near the middle, a result that made no sense if gravity were coming only from visible mass. The curves were flat, not falling. This implied a halo of invisible mass surrounding each galaxy, a cloud of dark matter extending far beyond the bright disk of stars. Since then, more evidence has piled up. Observations of the cosmic microwave background, the faint radiation left over from the early universe, show fluctuations that match models only when dark matter is included. Large-scale simulations of the universe's structure, tracing the formation of galaxy clusters and filaments, only work when dark matter provides the gravitational framework. Even gravitational lensing, the bending of light by mass, shows extra distortion that can't be explained by visible matter alone. What all this means is that dark matter is not just a theoretical placeholder. It's a real component of the universe, detectable through its influence. Wherever we look, in galaxies, in clusters, in the overall shape of the cosmos, we see its fingerprints. It holds galaxies together. It provides the scaffolding on which visible matter gathers. Without it, the universe as we know it would not exist. And yet we still don't know what dark matter is. It's not made of protons, neutrons, or electrons. It's not the same as the ordinary matter that forms people, planets, or stars. It may be made of exotic particles that interact very weakly, particles that pass through ordinary matter without being absorbed or deflected. Some theories suggest massive particles called WIMPs, weakly interacting massive particles. Others propose axions, hypothetical particles born in early universe conditions. There are even models involving sterile neutrinos or extra dimensions. Despite numerous experiments designed to detect dark matter directly, no particle has yet been observed. Sensitive detectors buried deep underground search for collisions between dark matter and ordinary nuclei, but so far they have found nothing definitive. That doesn't mean dark matter isn't there, only that it remains elusive. Its presence is known by what it does, not what it is. And yet this hidden substance controls so much. It shapes the way galaxies form, the way they spin, and the way they cluster. It affects the timing of structure formation in the early universe. It determines the path of light across the cosmos, bending and distorting it even when no visible object is present. It sets the architecture of space itself. In the Milky Way, our own galaxy, dark matter forms a vast spherical halo, extending far beyond the stars we see. Earth, the Sun, and everything else we know moves through this invisible field. It is all around us, and yet we do not feel it directly. It does not push or pull in any familiar way. Its only influence comes through gravity, subtle, pervasive, and always present. There is a kind of humility in this discovery. To realize that most of the universe is made of something we cannot see, something we do not understand, is a reminder that our senses, even extended by technology, offer only a limited window. We build theories, design detectors, and search for signatures, but so far, dark matter remains just beyond reach. And still we know it shapes the very framework of the cosmos. Without dark matter, galaxies would not form the way they do. The early clumps of gas and dust that gave rise to stars needed gravitational seeds to pull them together. Those seeds were provided by dark matter, collecting in dense regions, creating wells of gravity that attracted ordinary matter, helping galaxies take shape. Even today, as galaxies drift through space, they carry their dark matter halos with them, silent companions that define their boundaries and affect their interaction. When galaxy clusters collide, we can see visible matter, hot gas and stars, separate from where most of the gravitational mass lies. That separation is visible in cluster lensing maps, showing us where dark matter must be. Again and again, observations confirm its presence. It is not chaos, it is structure. It is not void, it is influence. As we continue to search for its identity, new experiments are being developed. More sensitive detectors, higher energy colliders, satellite missions that can map its gravitational effects with even greater precision. The goal is to find not only how dark matter behaves, but what it is made of, to transform it from invisible architecture into a known component of physical reality. Whether that discovery comes in the next decade or in the distant future, the evidence will remain. Dark matter is not a placeholder. It is a player in the cosmic story. And even in its silence, it speaks through the paths of galaxies, the bending of light, and the persistence of structure in an otherwise chaotic universe. It reminds us that not everything real is visible, and not everything invisible is unknown. Chapter 13. The number of stars outnumbers grains of sand. When you stand on a beach and look down at the sand beneath your feet, you're seeing something familiar, something physical, tiny and countless. The grains of sand slip between your fingers, cling to your skin, and stretch for miles across the shoreline. It's easy to believe that their number is beyond reckoning. Each handful contains thousands. Each stretch of beach holds billions. Every desert, every dune, every ocean floor, all packed with microscopic fragments of rock, shaped by time and water, too many to count. And yet, despite the unimaginable number of grains of sand on Earth, there is something even more abundant. Stars. Not just the stars you see in the night sky, though those alone are impressive. On a clear, dark night, far from city lights, you might glimpse a few thousand stars with the naked eye. Through a telescope you'll see more. But even the entire sky you can observe. Every glittering point represents only a tiny portion of what exists. The Milky Way, our own galaxy, is home to around 100 to 400 billion stars. That's just one galaxy, and there are not just a few hundred galaxies in the universe. There are hundreds of billions of them, each with its own collection of stars, planetary systems, and vast swirling formations of gas, dust, and dark matter. When astronomers added up the numbers based on deep sky surveys, they estimated that there are around 1 sextillion stars in the observable universe. That's a one. To say it plainly, there are more stars in the observable universe than there are grains of sand on every beach, in every desert, on every coastline of planet Earth. This comparison isn't poetic exaggeration. It's grounded in real scientific estimation. While the number of sand grains on Earth is somewhere around 7.5 times 10 to the 27 quintillion, 500 quadrillion, the number of stars exceeds that by a factor of 100 or more. That means for every grain of sand, there are dozens, even hundreds of stars. It's not just the quantity that stuns, it's the realization that each one of those stars is a sun, a vast, glowing sphere of fusion-powered plasma. Many of them are surrounded by planets, moons, asteroids, entire systems that may resemble our own. Some stars are bigger than our sun, many are smaller, and some exist in binary or trinary systems where multiple stars orbit a shared center of gravity. Each star is not just a point of light, it is a world maker. And these stars are not scattered randomly. They form galaxies, each with unique structures, shapes, and histories. Spiral galaxies with sweeping arms, elliptical galaxies filled with older stars, irregular galaxies shaped by collision. They orbit in clusters and superclusters, linked by invisible threads of dark matter spread out across the cosmic web. Between them lie vast voids, regions of almost total emptiness, where few stars or galaxies exist. Even in the observable universe, we've only mapped a fraction of these systems in detail. Some galaxies are so far away that their light has traveled for over 13 billion years just to reach us. We see them as they were in the distant past, before the Earth existed, before the Sun had formed, when the universe itself was still young. And the observable universe is only part of the story. Beyond the horizon defined by light's travel time, there may be more, possibly infinitely more. We don't know how big the universe is beyond what we can observe. But if space continues, and if it holds galaxies similar to what we see locally, then the true number of stars could be vastly greater than our current estimates. So what does it mean to live in a universe so rich in stars? A universe where every handful of sand on Earth is dwarfed by distant, burning suns. It means we are not central. Earth is not the only planet. Our sun is not the only light. It is one among many. A single spark in a vast sea of fire. The night sky is not dark. It is full. The darkness we see is simply the distance, the delay, the time it takes for that light to arrive. The stars do not all shine with the same brightness. Their color, size, temperature, and composition vary. Red dwarfs are small and cool, burning slowly for trillions of years. Blue giants are massive and hot, living fast and dying young. There are stars so faint we can barely detect them, and others so bright they light up entire regions of their galaxies. Some stars are forming now, born in cold clouds of gas collapsing under gravity. Others are dying, shedding layers or exploding in supernovae, leaving behind neutron stars or black holes. The life cycle of stars is constant. Some are young, some are ancient, some are alone. Others are part of dense clusters where thousands of stars are packed into small regions, and surrounding these stars are planets, exoplanets. Planets beyond our solar system have now been confirmed by the thousands. We have found gas giants, rocky Earth-like worlds, planets orbiting twin stars, and rogue planets drifting without a sun. Some systems have dozens of planets, others seem barren, but with so many stars the potential for diversity is beyond imagination. Each star may host its own story. Each may carry the conditions for weather, for chemistry, for evolution, maybe even for life. We don't know how common life is beyond Earth, but with such staggering numbers, the possibility remains. We are not alone in the dark, at least not in potential. When you look at a beach, when you see the uncountable grains beneath your feet, you're seeing something that feels immense. And yet, the universe reminds you that what feels infinite here is only a fraction of what exists. The real vastness lies above, not below, not on the ground, but in the sky. And you are part of that sky. You came from one of those stars. Your atoms were formed in their cores. Your energy, your light, your being, all rooted in fusion that happened long ago in a sun not unlike our own. You don't just live in a universe full of stars, you are made of their remains. As we continue, we'll keep exploring that legacy, how those stars form, how they die, and how the echoes of their lives shape everything we know. Because in a universe where stars outnumber the grains of sand, the story is still unfolding. Chapter 14. Time began at the Big Bang. But we don't know what came before. When we speak of the universe, we usually begin with a moment, a boundary in time known as the Big Bang. It's described as the origin of everything, the beginning of space, the birth of matter, the unfolding of energy. But what's less often understood is that according to the best models we have, the Big Bang wasn't just the start of space. It was also the beginning of time itself. It's a strange idea. We are so used to thinking in terms of before and after. Every event we know has a cause, a sequence, a history. When we tell stories, they have a beginning, a middle, and an end. So when we hear that the universe began 13.8 billion years ago, it's natural to ask, what happened before that? But that question runs into a problem. Not because we haven't found the answer, but because the question itself may not apply. Time in physics is not separate from space. Together they form a unified structure known as space-time. When the Big Bang occurred, it didn't happen in space. It was the beginning of space. And because space and time are bound together, the Big Bang was also the beginning of time. Not just of matter or energy or light, but of the very dimension in which events can occur, moments can pass, and causality can exist. That means asking what came before the Big Bang might be like asking what's north of the North Pole. The question assumes a direction, a dimension, that may not exist. The Big Bang may not have been an explosion in space, but rather the appearance of space and time from a condition that had no before. This idea doesn't come from guesswork. It arises from the equations of general relativity, Einstein's theory of gravity. When those equations are run backwards in time, they lead to a singularity, a point of infinite density and zero volume, where the curvature of space becomes infinite. At that point, the math breaks down. The familiar rules of physics no longer apply. That singularity marks the boundary of our known universe, not just in space, but in time. But there's a caveat. General relativity is a classical theory. It doesn't include the effects of quantum mechanics, which govern the behavior of matter and energy at the smallest scales. Near the singularity, those quantum effects are expected to become important. And because we don't yet have a complete theory of quantum gravity, a framework that unites quantum mechanics with general relativity, we cannot say for certain what happens at or before the Big Bang. Several proposals have been made. Some suggest that time may have extended before the Big Bang, but in a very different form, perhaps with different rules, or in a way that doesn't resemble time as we experience it. Others suggest that the Big Bang was not a beginning, but a transition, one phase of the universe giving way to another. There are theories involving cosmic bounce models, in which a previous universe collapsed in a big crunch, followed by a rebirth, a new expansion. In such models, the Big Bang is not the origin of all things, but a moment of transformation. Other ideas involve the multiverse, suggesting that our universe is just one bubble in a much larger sea of universes, each with its own laws, timelines, and constants. In those frameworks, the Big Bang may simply be the point where our bubble began, while others existed long before or continue elsewhere. And then there's the Hartle-Hawking model, proposed by James Hartle and Stephen Hawking, which describes time before the Big Bang as being more like a spatial dimension, one that becomes time-like only after a certain point. In that model, asking about before the Big Bang is like asking what direction is beyond the edge of a rounded surface. It's not that something is hidden there, it's that the question no longer has meaning. What we do know is that time as we measure it, seconds ticking on a clock, events unfolding one after another, began at the Big Bang. That's the moment when the laws of physics, the expansion of space, the cooling of energy, and the formation of matter began to operate in ways we can observe and understand. Before that point, if before even applies, lies mystery. It's not just a gap in knowledge. It's a frontier, a boundary where our theories reach their limits, and where new understanding is needed. The search for quantum gravity, the effort to unify our models of the very large with those of the very small, is, In part, an effort to look past that boundary, to find out what time really is, where it begins, whether it had a starting point, or whether time itself is an emergent property, arising from deeper laws we don't yet see. Some physicists believe time may not be fundamental, that it is not a basic feature of reality, but something that emerges from the relationships between things. That change gives rise to the illusion of time, but that at the deepest level there may be no ticking clock, only structure, interaction and relative state. If that's true, then the Big Bang may not be the start of time, but the start of something like time, a boundary where experience, direction and causality begin to make sense. Beyond it, the universe may exist in some other form, unmeasured and unmeasurable by the tools we have now. But even if we can't know what came before the Big Bang, we can learn about what happened after it. We can trace the early universe from that first instant of expansion, a searing, dense state, filled with energy cooling rapidly, forming particles, atoms, stars and galaxies. We can map its history, detect its echoes, model its growth, and in doing so we deepen our understanding of how time moves forward, even if we don't yet know where time came from. And maybe that's enough for now. To know that time is not just a given, but a phenomenon with structure and origin. To know that the seconds passing now, as you lie still, listening, resting, are part of a flow that began 30 years ago, and that carries you forward even as you sleep. In the chapters ahead, we'll continue following that flow, not back into the past, but outward into the structures time has made, the galaxies, the clusters, and the hidden architecture of space itself, because whatever came before, time is still unfolding, and we are within it. Chapter 15. The largest known structure in the universe is a supercluster. When we look up at the night sky, it's easy to imagine stars as isolated beacons, scattered evenly through the darkness, each twinkling alone in the vastness of space. But this picture is misleading. Stars gather into galaxies, galaxies group into clusters, and those clusters are part of something even larger, something vast, something that stretches so far and so wide that the numbers quickly pass beyond human scale. The largest known structure in the observable universe is called a supercluster. A supercluster is not just a group of galaxies. It is a group of galaxy clusters, each containing hundreds or even thousands of galaxies, all bound together by the gravity of invisible dark matter and shaped by the flow of cosmic expansion. These are regions of concentrated mass, surrounded by immense voids, regions where very few galaxies exist. Together they form a structure that resembles a web, a lattice, a sponge with filaments and gaps stretching across the universe. Our own galaxy, the Milky Way, is not isolated. It is part of a small group of galaxies known as the local group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller satellite galaxies. This local group in turn is part of a larger cluster, the Virgo cluster, which contains thousands of galaxies packed more densely together. But even this cluster is not the largest scale of structure. The Virgo cluster itself is only one small part of the Liniaceae supercluster, the enormous structure we now understand as our home in the cosmic web. Liniaceae, a Hawaiian word meaning immense heaven, was named to reflect its extraordinary scale. Liniaceae spans more than 500 million light-years. That means, if you were to shine a beam of light across its diameter, it would take more than 500 million years to travel from one end to the other, and it contains more than one. This vast collection of galaxies, galaxy groups, and galaxy clusters is not a random scattering of matter. It forms streams and flows shaped by gravity, moving slowly over time toward massive gravitational attractors, dense regions where the concentration of dark matter and galaxies is especially high. One such attractor is the Great Attractor, a mysterious region pulling galaxies toward it from across Liniaceae, including our own. Even more massive is the Shapley supercluster, another gravitational heavyweight located over 650 million light-years away. It's one of the most massive known structures in the universe, with enough mass to influence the movement of entire clusters in its direction. These enormous structures act like anchors in the cosmic web, concentrating matter, bending space, and drawing everything near into their grasp over billions of years. But how do these massive structures form? To answer that, we return to the early universe. In the first moments after the Big Bang, space was nearly uniform. Almost the same temperature, almost the same density, almost tiny variations in energy and mass, smaller than a 1 in 100,000 difference, were imprinted into the early plasma. These slight irregularities caused by quantum fluctuations during inflation acted like seeds. As the universe expanded and cooled, gravity began to amplify those variations. Regions with just a little more mass began to attract more matter. Over time, these regions grew, becoming the first halos of dark matter. Gas followed, cooled, condensed, and formed stars. Small galaxies formed first, then merged into larger galaxies, then collected into groups and clusters. Eventually, clusters were pulled into larger networks, aligned along invisible filaments formed by dark matter. These filaments are not theoretical. We can map them through gravitational lensing and large-scale survey. The Sloan Digital Sky Survey, the 2-degree field galaxy redshift survey, and others have created maps showing how galaxies align into long thread-like structures with great voids in between. The result is what we call the cosmic web, an enormous network of superclusters, filaments and voids. And in that web, superclusters are the densest intersections. They are the cities in the landscape of the universe, vast metropolises of matter, connected by intergalactic highways of gas and dark matter, expanding ever outward with the cosmos itself. But even superclusters are not eternal. Over immense periods of time, expansion weakens their bonds. Some regions of superclusters may eventually drift apart. Others, more tightly bound by gravity, may collapse inward, merging into massive elliptical galaxies or central black holes. The future shape of superclusters depends on the tug-of-war between gravity and dark energy, between collapse and acceleration. Still, for now, they exist as the largest coherent structures we've observed. When you zoom out far enough, the distribution of galaxies begins to show pattern. Clusters here, gaps there, flows of movement, converging points, all of it arranged in a way that reminds some scientists of neural networks, or foam, or coral reefs. Structures that seem organic, almost alive. And within one corner of that structure, our Milky Way drifts silently, carried on a river of gravity inside Laniakea, orbiting its center every few billion years, its stars and planets turning gently in the quiet flow of galactic motion. From our tiny perspective on Earth, it's hard to grasp that we are part of something that large. We see the night sky as individual stars. We speak of constellations and patterns, but those are local features, mere sketches on the inner wall of a single galaxy. The full picture is far grander. The space around us is structured not by coincidence, but by forces that span hundreds of millions of light-years. We are not floating alone. We are part of a structure, a filament, a cluster, a supercluster. A single strand in a cosmic web that stretches across the observable universe. And yet, as massive as these superclusters are, they may still be only the beginning. With every generation of telescopes, we look farther and see more. Some of the structures we now observe are so large that they challenge our understanding of cosmic uniformity. Giant quasar groups, massive walls of galaxies, great arcs of matter, bending across space in patterns still not fully explained. So the story of structure in the universe is not finished. We are still learning what the largest pieces look like, how they formed, and what they tell us about the shape and future of the cosmos. As we move into the next chapter, we will explore another strange feature of this cosmic architecture, not a cluster, but a gap. Because just as there are immense structures holding galaxies together, there are also immense voids, where almost nothing at all exists. Chapter 16. There's a giant void in the universe that's 1.8 billion light-years across. In previous chapters we explored some of the largest structures known to science, superclusters that stretch across hundreds of millions of light-years, bound by gravity and filled with thousands of galaxies. But the universe is not evenly filled. It does not spread matter like paint across a canvas. Instead, it arranges galaxies into filaments, walls and clusters, and leaves behind vast, cavernous spaces where almost nothing exists. These are the cosmic voids, and among them is one so large, so empty and so mysterious that it still challenges astronomers today. It is called the Giant Void, and it spans an estimated 1.8 billion light-years across. To put that in perspective, consider that the Milky Way galaxy, our entire galactic home, is about 100,000 light-years wide. The Giant Void is 18,000 times larger. Light, traveling at its maximum speed, would take nearly 2 billion years to cross it. In that time, all of human civilization, from the first stone tools to modern physics, would come and go many times over. And even then, the beam of light would still be crossing empty space. This enormous void is located in the constellation Canes Venatici, a quiet region of the sky where few galaxies appear. Surveys show that the density of galaxies in this area is far below the cosmic average. Where one would expect to find clusters, filaments, or galaxy walls, there is instead silence, an absence, not total darkness, but a profound lack of structure. Voids like this one are not completely empty. They contain sparse gas, dark matter, and the occasional galaxy, but their density is significantly lower than that of surrounding regions. In the case of the Giant Void, the galaxy population is so low that it has become one of the most extreme examples of underdensity ever discovered. The existence of voids was first confirmed in the late 20th century. As galaxy surveys grew more precise, astronomers began to map the three-dimensional distribution of galaxies, using redshift data to determine distance. What they found was surprising. Galaxies were not scattered uniformly, but arranged in a sponge-like structure, now called the cosmic web, with clusters and filaments surrounding vast, bubble-like regions that were nearly empty. The Giant Void is one of the largest of these bubbles. Its discovery raised questions about how such a massive underdense region could have formed. According to standard models of cosmology, small voids are expected. They arise naturally as matter collapses into denser regions, leaving behind gaps. But the sheer size of this void suggests that rare conditions must have shaped it. Perhaps the initial distribution of matter in that region was unusually smooth, or perhaps early cosmic inflation created fluctuations that exaggerated the gap. Either way, it remains an active subject of study. What's even more intriguing is that the Giant Void may not be alone. Other extremely large voids have been found, though few reach the same scale. One particularly famous example is the cold spot, a region of the cosmic microwave background radiation that is cooler than expected. Some researchers have suggested that this cold region might correspond to a vast void in space, an area where the lack of matter has slightly altered the path and energy of ancient photons on their way to Earth. Though this connection is still debated, it highlights something important. Voids are not just visual gaps. They affect the flow of energy, light, and matter. Photons passing through a void experience subtle changes in redshift. Large voids can lens light, distort galaxy maps, and influence the structure of space around them. They may even offer clues about the behavior of dark energy, the mysterious force driving the accelerated expansion of the universe. But beyond their scientific importance, voids offer something else. A sense of scale that is difficult to grasp. We often think of the universe as full of stars, galaxies, planets, motion, and heat. But the truth is, emptiness dominates. Space is not packed. It is mostly vacuum. And the structures we observe, as vast as they are only small islands in a sea of quiet. The giant void is one such sea, a region where galaxies are rare, where motion slows, and where even light passes undisturbed for billions of years. It's a place where the universe whispers instead of shouting, and it reminds us that nothingness is not failure or absence, but a fundamental part of the cosmic design. We sometimes equate value with presence, more stars, more planets, more light. But the giant void shows that the universe also builds meaning from contrast, from space, from distance, from silence. Just as the quiet between notes creates music, the emptiness between galaxies creates structure. Without voids, clusters would have no shape. Without gaps, walls would not stand. Without silence, motion would have no rhythm. And though we will likely never visit these voids, they are too vast, too remote, too empty. They are part of the same universe that we inhabit, the same cosmos that formed the Earth, the Sun, and the thoughts you are having right now. You exist not outside of these structures, but within them. And just as you are shaped by atoms forged in stars, you are also part of a universe where space itself stretches into nothing for light years at a time. In the next chapter we will return from emptiness to something dense, compact, mysterious, and heavy beyond comprehension. Because not all quiet places are vast. Some are small, some are dense, some bend time itself. Chapter 17. Saturn's rings are younger than the dinosaurs. When you look at Saturn through a telescope, even a small one, its rings are the first thing you notice. They're unmistakable. Glorious arcs of pale light encircling the gas giant, hovering like a celestial halo suspended in space. To the human eye, they seem perfect, ancient, eternal, as if they've always been there, turning quietly in the dark for billions of years. But they haven't. In fact, according to the latest research, Saturn's rings may be incredibly young. So young, in fact, that they didn't even exist during the time of the dinosaurs. This is one of those facts that surprises almost everyone the first time they hear it. After all, Saturn is over 4.5 billion years old. The planet formed early in the solar system's history, likely around the same time as Jupiter, as massive clouds of gas collapsed and coalesced. For most of scientific history, it was assumed that the rings, so large, so elegant, were a remnant of that formation. A leftover, a cosmic fingerprint from the solar system's childhood. But as scientists studied the rings more closely, that assumption began to unravel. Observations from NASA's Cassini spacecraft, which orbited Saturn from 2004 to 2017, changed everything. Cassini didn't just take pictures, it flew directly through the rings, sampled their particles, measured their mass, and recorded their behavior in exquisite detail. What it found was that the rings are made primarily of water ice. Not just ice, but pristine, bright ice, far too clean and unweathered to be billions of years old. Over time, space is messy. Micrometeorites and cosmic dust constantly bombard objects in orbit. Surfaces get darkened, pitted, and covered with debris. For Saturn's rings to look so clean, they must be relatively recent. If they had been around for billions of years, they'd be darker, more polluted, less reflective. Instead, they remain brilliantly bright, reflecting sunlight with surprising efficiency. Cassini also measured the rings' mass and found that they're surprisingly light. Their total mass is just a fraction of Saturn's moon Moima. For something so visually stunning, their physical heft is small. This too suggests youth. A massive, ancient ring system would have evolved differently. Heavier rings might have lasted longer, grown darker, collapsed into moons, or spread out more over time. The current ring system appears delicate, temporary, and so scientists began to recalculate their age. The numbers kept coming back younger than expected. Some estimates place their formation at just 100 million years. That means the rings appeared well after the age of the dinosaurs had begun, and possibly even after they had gone extinct. In a universe that measures time in billions, Saturn's rings may be no older than the Alps, no older than flowers, no older than birds. So how did they form? There are several leading theories. One of the most likely involves the destruction of a former moon. Perhaps a large, icy moon, one roughly the size of Moimas or even larger, strayed too close to Saturn's powerful gravity. Once inside the planet's Roche limit, the distance within which tidal forces overcome self-gravity, the moon would have been torn apart. Its icy outer layers shredded into particles. Those particles then spread out into a flat, thin disk, coalescing into the elegant ring system we see today. Another possibility is that a large comet or Kuiper belt object collided with an existing moon, smashing it apart and scattering its remains. The timing of such an impact would have to be just right. Not too early, or the rings would have already aged and darkened. Not too recent, or we might still see remnants of the original collision. Whatever the cause, the result was a ring system unlike any other in the solar system. Other planets have rings. Jupiter, Uranus, and Neptune all wear faint halos, but none are as spectacular as Saturn. None are so wide, so bright, so intricately structured. Some rings are narrow, others are broad. There are gaps, waves, resonances, and braids. Some are shepherded by tiny moons whose gravitational tugs maintain the ring's edges and shapes, and all of it, this entire system, may be temporary. That's another surprising realization. Just as the rings are young, they are also disappearing. Cassini's final observations detected a process scientists call ring rain. Tiny particles from the rings are falling into Saturn's atmosphere. Slowly, steadily, they spiral down, drawn by gravity and influenced by Saturn's magnetic field. Each year, thousands of kilograms of material are lost. It's a drizzle of ice and dust, invisible from Earth, but relentless. Estimates suggest the rings could be completely gone in as little as 100 million years. That may seem like a long time, and to us it is, but in planetary terms it's fleeting. We just happen to live in a golden window, a narrow slice of time when Saturn wears a crown of ice. Before that crown existed, there was nothing but the bare planet, and in the distant future, there will be nothing again. Just Saturn, ringless, quiet, spinning alone. This moment, our moment, is rare. There is something poetic about that. We live in a universe that is not fixed, not static, not frozen. Even the things that feel timeless are in motion. Stars are born and die. Galaxies collide. Planets change. Rings form and disappear. The sky is not a portrait. It is a living process, and like all living things, it changes. So the next time you see Saturn through a telescope, remember that you are witnessing something fleeting, a celestial phenomenon that did not exist when the first dinosaurs walked the Earth, a formation so young that in the lifespan of stars, it is practically a newborn. You are living during the age of Saturn's rings. One day, perhaps far in the future, someone else will look at Saturn and see only the smooth curve of its atmosphere. No rings, no halos, no icy arcs, just a memory in books and data. But for now, in our age, in this moment, Saturn still wears its crown, and in the chapters ahead, we'll continue exploring just how much of the solar system and the universe is constantly changing, because the cosmos does not stand still. It never has. Chapter 18. Black holes aren't empty. They're the densest objects in the universe, To many people, a black hole sounds like a hole in space, a void, a cosmic drain, something that swallows and disappears. But that idea, while poetic, is misleading. A black hole is not a hole. It is not empty. It is, in fact, the opposite of empty. It is the densest form of matter known to science. A black hole begins as a star, not just any star, but a massive one, many times the mass of our sun. When that star reaches the end of its life, it can no longer generate the outward pressure needed to resist its own gravity. Fusion halts. The balance breaks. And in an instant, gravity wins. The core collapses. But this collapse doesn't stop at a dense ball of matter. It keeps going. The matter gets crushed, tighter and tighter, far beyond anything familiar, beyond atoms, beyond protons, beyond the very concept of volume. It reaches a point where the density becomes infinite. Not metaphorically infinite, but mathematically infinite, according to general relativity. A point of zero size and limitless density. A singularity. Surrounding this singularity is the event horizon, the boundary where escape becomes impossible. Not even light, traveling at its maximum speed, can get out. This is what makes the black hole black. Not because it's empty, but because its gravity is so intense that nothing, not even photons, can escape once they cross that invisible line. But inside that event horizon lies not a void, but all the mass that collapsed to create it. A black hole is full of gravity, full of curvature, full of information. It's not a nothing, it's a somewhere we cannot reach, cannot see, and cannot currently understand. Black holes come in several sizes. The smallest ones, stellar mass black holes, form from individual stars and weigh several times the mass of the Sun. Then there are intermediate mass black holes, which are rarer and harder to detect, but may exist in clusters. At the center of most galaxies, including our own, lie supermassive black holes, millions to billions of solar masses, packed into regions no larger than a solar system. These giants may have formed early in the universe, growing through mergers and feeding on surrounding matter for eons. And yet, for all their mass, black holes are not wide. Their size is determined by something called the Schwarzschild radius, which is the distance from the singularity to the event horizon. For a black hole the mass of our Sun, that radius is just 3 kilometers. Compress the Sun, which is over 1 million kilometers across, into a sphere 3 kilometers wide, and you have a black hole. That compression, that collapse, is what makes a black hole dense, not because it contains more matter than usual, but because it squeezes that matter into impossibly tight space. And this compression curves space-time so sharply that the rules we take for granted break down. But how do we know they exist? Black holes cannot be seen directly, but they leave signatures. We detect them by watching the behavior of nearby stars, stars that orbit invisible points. We see them by the X-rays emitted when matter falls into the accretion disk, the swirling spiral of gas heated to millions of degrees before vanishing past the event horizon. We've even imaged one. In 2019, the Event Horizon Telescope released the first real picture of a black hole's shadow, captured in a galaxy called M87, 55 million light-years away. That glowing ring, the result of light warped and trapped near the event horizon, is not science fiction. It's real, and it confirmed what had only existed in equations for over a century. Despite their fearsome reputation, black holes do not suck in everything around them. A black hole with the same mass as the Sun would exert the same gravitational pull from a distance. You could safely orbit it, just like Earth orbits the Sun. The danger comes only when you get too close, when you pass the event horizon. At that point, escape becomes impossible. What happens inside? We don't know. This is one of the great mysteries of modern physics. General relativity says the singularity is a point of infinite curvature. Quantum mechanics says infinities are unphysical. Somewhere in that contradiction lies a deeper truth, one that requires a new theory of gravity, one that unifies the small and the large. Some ideas suggest that information falling into a black hole is not lost. It's preserved on the surface of the event horizon, encoded like a hologram. This is known as the holographic principle. Others propose that black holes might evaporate over time, slowly leaking radiation, as predicted by Stephen Hawking. If so, then black holes are not eternal. Over trillions of years, they may shrink and vanish. Even the giants at the centers of galaxies may eventually dissolve into faint whispers of energy. But until then, they remain massive, invisible anchors shaping galaxies, curving space-time, dictating the motion of stars. They are not objects in space. They are regions of space, bent so intensely that time itself behaves differently near them. Near a black hole, time slows. An observer hovering just above the event horizon would experience time differently than someone far away. Minutes near the horizon could equal centuries outside. This isn't theory. It's a prediction confirmed by general relativity and supported by experiments involving clocks and satellites. Time is not absolute. Near a black hole, it bends. In some speculative models, spinning black holes may even create pathways, wormholes, tunnels through space and time, but these remain unconfirmed and highly theoretical. Still, black holes show us what space-time is capable of. They are not just objects, they are phenomena, not things in the universe, but shapes the universe can take. And when you look up at the stars, understand that many of them will one day become black holes. The most massive among them will collapse, vanish behind event horizons, and continue shaping the cosmos silently. Even now, millions of black holes drift through our galaxy unseen, ancient, waiting. They are not empty, they are full, and they remind us that space is not passive. Space has structure, curvature, power. It can twist, warp, stretch, and collapse. In the chapters ahead, we'll keep exploring how that structure builds everything we see, from the smallest particles to the grandest forces, to the very expansion of the cosmos itself. Chapter 19. Neutron stars are so dense, a teaspoon weighs 1 billion tons. In the universe, size doesn't always mean strength. Some of the most powerful objects in existence are also the smallest. You might picture galaxies, supernovae or black holes when you think of cosmic intensity, but there is another kind of object, one that doesn't bend light to invisibility like a black hole, yet still pushes matter to its most extreme form. It is called a neutron star, and it is so dense, so compressed, that a single teaspoon of its material would weigh over 1 billion tons. Let that settle in. 1 teaspoon. The same volume you might use to stir sugar into your tea. But instead of sweet crystals, imagine that tiny spoon filled with the crushed remains of a star. And now imagine that material weighing more than every building on Earth combined. That is the density of a neutron star, the collapsed core left behind after a massive star explodes. Here's how it happens. When a massive star reaches the end of its life, it burns through its nuclear fuel, layer by layer, hydrogen into helium, helium into carbon, all the way up to iron. But once iron forms in the core, the star can no longer extract energy through fusion. Gravity, unopposed, takes over. The core collapses. In this collapse, protons and electrons are squeezed together into neutrons. The result is a dense, compact ball composed almost entirely of neutrons, hence the name neutron star. This object is incredibly small by stellar standards. A typical neutron star is only about 20 kilometers across, roughly the size of a city, and yet it contains more mass than the Sun. Compressing that much mass into that smaller volume creates an object with staggering gravitational pull. Surface gravity on a neutron star is about 100 billion times stronger than Earth's. If you were somehow standing on its surface, which you couldn't, you'd be flattened instantly. Even a small bump 1 millimeter high would require more energy to climb than Mount Everest here on Earth. Escape velocity exceeds half the speed of light. Space itself curves sharply around the star. And yet, despite all this intensity, neutron stars are real. We have detected them. They reveal themselves as pulsars, rapidly spinning neutron stars that emit beams of radiation like cosmic lighthouses. As they spin, their beams sweep across Earth, producing regular, repeating signals. Some pulse dozens or even hundreds of times per second, rotating faster than kitchen blenders. These pulses are so precise that astronomers use them as cosmic clocks. The fastest spinning pulsars, known as millisecond pulsars, can rotate more than 700 times per second. That means a dense ball the size of a city is spinning at thousands of kilometers per hour without breaking apart. The reason it holds together is the same reason it formed. Gravity. Immense, relentless, perfectly balanced gravity. And neutron stars are magnetic. Extraordinarily so. Some possess magnetic fields trillions of times stronger than Earth's. These magnetic monsters are called magnetars, and they occasionally produce bursts of gamma rays, so intense they can be detected across the galaxy. A single flare from a magnetar in 2004 momentarily altered Earth's ionosphere from over 50,000 light-years away. We've even seen neutron stars collide. In 2017, the LIGO and Virgo observatories detected gravitational waves from a binary neutron star merger. Two of these dense remnants had spiraled into each other over millions of years, and when they finally collided, they produced a flash of light, a burst of gamma rays, and ripples in space-time itself. It was a moment of extraordinary significance. Not only did it confirm Einstein's predictions, but it also gave us clues about the origin of heavy elements. Because when neutron stars merge, the extreme conditions can forge elements heavier than iron, like gold, platinum, and uranium. That's right, some of the gold in your jewelry, some of the atoms in your body, were likely born in the explosive death or collision of neutron stars. These tiny, ultra-dense stars are not just astrophysical curiosities, they are furnaces, clocks, lighthouses, laboratories of extreme physics. They are the bridge between ordinary matter and the limits of our understanding. A neutron star sits just this side of becoming a black hole, its gravity enormous, but not enough to collapse into a singularity. It is a balance, matter pushed to its maximum before it disappears behind an event horizon. And if you were to touch a neutron star, not that you could, you'd find that the material is no longer atomic. Atoms don't survive such pressure. Electrons have merged with protons. Neutrons are packed side by side like grains of sand in a fortress, a trillion times stronger than steel. The crust of a neutron star, a thin shell of exotic material, may be the hardest substance in the universe. Beneath it, the density increases. Some theorists believe that at the center, the neutrons may dissolve into a soup of quarks, the fundamental building blocks of matter. If so, then neutron stars might be hiding quark matter, or even strange matter, inside their cores, substances we cannot create on Earth, but which may exist naturally in these cosmic remnants. It's hard to imagine how something so small can contain so much, but that's the lesson of the universe again and again. Scale is deceptive. Immensity is not always visible. The most powerful things can be quiet. The most extraordinary truths can be hidden in small, unremarkable shells, drifting through space. And in the stillness of a neutron star, we find that the cosmos is not only vast, it is deep. A teaspoon, a billion tons, a single moment in a stellar life, frozen in collapse, still pulsing with energy. In the next chapter, we'll widen our lens again, stepping out of the dead stars and dense cores to look at something even larger. Because if stars can collapse into points, the universe can expand without limit. Chapter 20. The universe is expanding faster than we thought. For most of human history, the night sky seemed still. The stars held their places. The constellations stayed fixed. The heavens appeared eternal, motionless, a quiet ceiling of lights that turned slowly with the seasons. But in the early 20th century, that perception changed forever. We discovered that the universe is not static. It is expanding. This idea, once radical, is now central to cosmology. In 1929, Edwin Hubble observed that distant galaxies are moving away from us, and the farther away they are, the faster they recede. This was not a sign that Earth is at the center, but evidence that space itself is stretching in every direction. Imagine dots on the surface of a balloon. As the balloon inflates, the dots move apart, not because they are moving themselves, but because the surface they rest on is expanding. This is how galaxies behave in space. The space between them grows, and that expansion has continued since the Big Bang. But recently, astronomers have noticed something surprising. The universe isn't just expanding. It's expanding faster than our models predicted. This discrepancy has come to be known as the Hubble tension. And it's not a small detail. It may be pointing to something missing or something fundamentally new in our understanding of the cosmos. Here's what's happening. There are two primary ways scientists measure the rate of cosmic expansion, a value called the Hubble constant. The first involves looking at the early universe, using observations of the cosmic microwave background radiation, the faint glow left over from the Big Bang. Instruments like the Planck satellite have mapped this glow with incredible precision. From this data, scientists use physical models to calculate what the current rate of expansion should be today. That's one method. The second involves looking at the modern universe directly. Astronomers observe supernovae and Cepheid variable stars in relatively nearby galaxies. These serve as standard candles, objects of known brightness, allowing scientists to measure distances and calculate how fast those galaxies are moving away from us right now. Both methods are precise, both are respected, but they yield different answers. The early universe method predicts a Hubble constant of about 67 kilometers per second per megaparsec. That means every megaparsec of distance, roughly 3.26 million light-years, adds 67 kilometers per second of speed to a galaxy's motion away from us. But the local universe measurements, those based on direct observation, suggest a higher value around 73 kilometers per second per megaparsec. That's not a trivial difference. The gap between these two values is too large to be explained by measurement error. It's not just noise in the data. It's a real, repeatable tension. And it suggests that something about our current model of the universe, the lambda cold dark matter model or LCDM, may be incomplete. Why would the expansion rate differ? There are several possible explanations. One idea is that something changed after the era of the cosmic microwave background. Perhaps a new force or form of energy emerged, something not yet accounted for in our equation. Others speculate that dark energy, the mysterious force driving the universe's acceleration, might not be constant. Maybe it's evolving over time. Perhaps it grows stronger with distance, or behaves differently depending on the structure of space. There's even the possibility of new, undiscovered particles. Some have proposed the existence of early dark energy, a temporary force that affected the rate of expansion shortly after the Big Bang. Others suggest modifications to gravity itself. If general relativity isn't the complete picture, the rules that govern expansion could change across cosmic scales. And of course, there's always the chance that both measurements are correct, and our assumptions about the universe's geometry or contents are flawed. Perhaps we are interpreting the data through the wrong lens, like trying to read a map without realizing the scale has shifted. What makes this tension so fascinating is not just the mystery, but what it implies. The fact that we don't know why expansion is faster is not a failure. It's a signal, a quiet indication that there is more to discover. Every time our predictions break from observation, we are pushed to look deeper, ask new questions, and refine the foundations of physics itself. And the expansion of the universe is not just a theoretical curiosity, it has real consequences. The faster the universe expands, the younger it appears. The timeline of galaxy formation, the development of structure, even the future fate of space, all depend on the rate of expansion. If that rate is increasing, the universe will continue growing colder, darker, and more diffuse. Galaxies will drift further apart, stars will die, and in the far future, even light from nearby galaxies may become unreachable. This is not something that happens quickly. These are changes measured in billions of years, but they remind us that the cosmos is not static, it's not fixed, it evolves. It transforms, and we, observers in a fleeting window of clarity, are watching it unfold. Just as the earth spins beneath our feet, just as the sun arcs through the sky, the universe itself is stretching, silently, without friction, without sound. Every second, more space is created between the galaxies. Every moment, the cosmos grows. Even now, as you lie still, listening, breathing, perhaps resting, the space between galaxies is increasing. The expansion continues, not with noise, but with grace. In the next chapter, we will step away from this outward motion and look inward again at something not seen with the eyes, but with detectors built to listen for ripples in the very fabric of space. Because while light reveals where things are, gravitational waves reveal how space itself moves. Chapter 21. Gravitational waves are ripples in the fabric of space-time. Most of what we know about the universe comes from light, from the glow of stars, from the dim shimmer of galaxies, from the afterglow of the Big Bang itself. For centuries, astronomy meant looking up and collecting light, with telescopes, with spectroscopes, with satellites tuned to every wavelength. But light is not the only messenger the universe sends us. There is another, more subtle, more delicate, a signal that doesn't travel through space, but is made of space itself. That signal is called a gravitational wave, and it is not a metaphor. Gravitational waves are real, physical ripples, distortions in the very shape of space and time. They move out from their source like waves on a pond. But unlike water, they don't just shake matter, they stretch and squeeze the fabric of reality itself, not across just one direction, but across dimensions. When a gravitational wave passes through, space is slightly compressed in one direction and stretched in another. The change is tiny, unimaginably small, but it is there. The idea of gravitational waves dates back over a century. In 1916, Albert Einstein predicted them as part of his theory of general relativity. According to this theory, mass bends space, and accelerating masses, especially massive ones, should send ripples through that curvature. But for decades, these waves remained theoretical. No instrument was sensitive enough to detect them. Until recently, in 2015, after years of development, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, made the first direct detection of gravitational waves. The signal came from a pair of colliding black holes, over 1 billion light-years away. These two giants had spiraled inward over eons, drawing closer, moving faster, until finally merging into one. In that final moment, a portion of their mass was converted, not into light, not into heat, but into pure gravitational energy ripples that stretched across the cosmos and reached Earth. LIGO's twin detectors, located in Louisiana and Washington state, use laser interferometry to measure changes in lengths smaller than the width of a proton. When a gravitational wave passes through Earth, it alters the distance between suspended mirrors in a precisely controlled vacuum. The result is a signal that captures a kind of motion unlike any seen before, not the motion of objects through space, but the motion of space itself. That first detection on September 14, 2015, confirmed Einstein's prediction and opened a new era in astronomy. For the first time, we could not just see the universe, we could listen to it. And what we heard was powerful. Gravitational waves allow us to detect events that produce no light at all. Black hole collisions, for example, are invisible in traditional telescopes. They do not emit radiation. They happen in darkness, but they shake the universe. Their waves travel unimpeded, unaffected by gas, dust, or electromagnetic interference. They carry a clean signal from the moment of impact, undistorted by the medium of space. Since that first detection, dozens of gravitational wave events have been recorded, including not just black hole mergers, but also neutron star collisions. These events are even more dramatic. When two neutron stars spiral into each other, they not only emit gravitational waves, they also produce light. The 2017 detection of such an event, labeled GW7U817, was the first time both gravitational waves and electromagnetic radiation were observed from the same cosmic explosion. This multi-messenger astronomy is now one of the most exciting frontiers in science. It lets us combine light and gravity to build a fuller picture of the universe's most violent moments. We can study how matter behaves under extreme pressure. We can trace the origin of heavy elements. We can test the limits of physics in ways never before possible. And as our detectors improve, so will our reach. Gravitational waves are not limited to the cataclysms of black holes. In the future, we hope to detect the subtle waves from white dwarf binaries, from early supernovae, even perhaps from the inflationary epoch shortly after the Big Bang itself. Some signals may carry information from times and places where light can no longer reach us, moments hidden behind clouds of plasma or buried in epochs of high density. But gravitational waves pass through everything. They are nearly impossible to block. They are whispers from the deep structure of space-time. The instruments that detect them, LIGO, Virgo, CAGRA, and soon LISA, a planned space-based detector, are among the most sensitive tools ever built. They must isolate vibrations smaller than an atomic nucleus, shielded from earthquakes, wind, and even the motion of molecules in the air. It is science at the edge of possibility, but it's working. We are now listening to the universe in a way our ancestors could never have imagined. And what we hear is not just random noise, it's rhythm, timing, echoes. Every chirp in the detector represents the final moments of a cosmic dance that lasted millions or billions of years. The last orbit, the collision, the merger, a conversion of mass into gravity, sent out in waves that travel through space not for seconds but for forever. Even now, gravitational waves are washing over you. Every second, the Earth is nudged and stretched by signals from distant collisions. You don't feel them, you don't hear them, but they are real, and they are passing through you right now. They stretch your body by a length less than a proton's width, and then release. You are living in a universe that moves, not just with light, but with rhythm. In this movement we find new ways to understand gravity, not just as a force, but as a shape, a geometry, a fluidity in space and time that responds to mass, energy, acceleration. When something massive moves, space-time moves with it. That is what gravitational waves are. In the next chapter we'll step from these ripples in the cosmos to something else that has a rhythm, the heartbeat of our sun, and how its cycles shape not only space but life on Earth. Chapter 22. The sun has a pulse, and it affects the entire solar system. We tend to think of the sun as a constant. It rises every morning, warms the planet, lights the sky, and sets again with near-perfect regularity. Its presence defines the rhythm of our lives, but beneath that brightness, beneath the steady glow that seems unchanging. The sun is not still. It is a dynamic, churning, breathing star. And just like a living organism, it has a pulse. Not a heartbeat like yours, not a thump in a chest, but a deep, powerful rhythm of magnetic activity that rises and falls in cycles. The most familiar of these is the solar cycle, a period of approximately 11 years in which the sun's magnetic field flips, rearranges and resets. This cycle affects everything from solar storms to Earth's climate to the behavior of satellites in orbit. It's not just a quirk of astronomy, it's a pulse that touches the entire solar system. At the core of the sun, hydrogen atoms are fused into helium under enormous pressure and heat, producing the energy that powers the sun's light. But that energy doesn't move directly outward. It takes hundreds of thousands of years to travel from the core to the surface, and as it moves, it stirs the sun's interior. Hot gases rise and fall. Magnetic fields twist and tangle. The sun's outer layers, particularly the convective zone and the photosphere, are in constant motion. This motion generates powerful magnetic forces. Over time, these forces grow more complex, looping through the solar atmosphere, creating sunspots, solar flares and coronal mass ejections. The entire process follows a roughly 11-year cycle, known as the solar activity cycle. At solar minimum, the sun's surface appears calm. There are few sunspots, few flares, and minimal outbursts. But as the cycle advances, magnetic activity increases. Sunspots multiply. Solar flares erupt with greater frequency. Gigantic plumes of plasma, called coronal mass ejections, are launched into space. At the height of the cycle, called solar maximum, the sun is at its most turbulent, and then it resets. The magnetic poles flip. North becomes south. The activity begins to decline. The cycle returns to quiet. This cycle has been observed for centuries. Early astronomers tracked sunspots and noticed their periodic rise and fall. Today, we measure the solar pulse using not just visual observation, but satellites like ISOHO, STO, and Parker Solar Probe, which dive close to the sun and collect real-time data about its surface, magnetic field, and solar wind. And this pulse isn't isolated to the sun alone. It reaches outward, carried by the solar wind. A continuous stream of charged particles that flows from the sun's outer atmosphere, or corona, and travels through space at hundreds of kilometers per second. This wind carries the sun's magnetic field across the entire solar system, shaping a giant bubble known as the heliosphere. Every planet, including Earth, orbits within this bubble. As the sun's activity waxes and wanes, so does the strength and structure of the solar wind. During solar maximum, the wind intensifies, becomes more erratic, and carries stronger magnetic fields. These fields interact with planetary atmospheres, including ours. They create auroras, disrupt communications, affect power grids, and even alter the flight paths of satellites. Solar storms, especially the powerful coronal mass ejections, can hurl billions of tons of charged particles toward Earth. When they arrive, they can compress our planet's magnetic field, inducing currents that surge through wires and pipelines. The largest known event, the Carrington event of 1859, caused telegraph systems to spark and fail, even before the age of modern electronics. If such a storm struck today, it could temporarily disable satellites, GPS systems, and even knock out sections of electrical grids. That's why space agencies monitor the sun constantly. Solar weather is not a curiosity, it's part of space's influence on Earth. And beyond Earth, this pulse reaches even farther. The solar wind defines the boundary of the solar system. At a certain distance, over 120 astronomical units away, it encounters the interstellar medium. Here, the solar wind slows and forms a shockwave, like a boat entering deeper water. This boundary, called the heliopause, is where the sun's influence ends. Beyond it lies the space between stars. The Voyager 1 and Voyager 2 spacecraft have both crossed this boundary. As they did, they recorded changes in particle density, magnetic orientation, and radiation levels. Even at these extreme distances, the memory of the Sun's pulse persists. But the 11-year solar cycle is not the only rhythm. There are longer cycles too, centennial and millennial variations in solar output that may be tied to larger patterns in Earth's climate. During the Maunder minimum, from about 6045 to 1715, sunspot activity nearly ceased. This coincided with a period of cooler temperatures in parts of the northern hemisphere, sometimes called the Little Ice Age. The exact connection between solar variability and climate is complex and still under study. But it reminds us that the Sun, though stable on human timescales, is not fixed. Its brightness, its magnetism, its storms, they all change with time. And these changes affect life. From migration patterns in animals, to weather, to technology, to radiation levels at high altitudes. The Sun's pulse is felt. It synchronizes the movement of particles, drives chemical reactions in the upper atmosphere, and even affects the reliability of radio transmission. Yet to the unaided eye, none of this is visible. The Sun still appears as it always has, a golden disk rising and falling in our sky, warm, familiar, quiet. But now you know there is motion underneath, there is turbulence, a hidden rhythm that shapes the space around us, and this rhythm, though vast, is part of a larger truth. The solar system is not just held together by gravity, it is bound by influence, by energy, by pulses of magnetism and waves of plasma that flow outward from a single star. The Sun breathes, and its breath moves through everything we know. In the next chapter, we'll go deeper into the unseen fabric that holds not just our star system, but the universe itself, the invisible force that shapes galaxies, bends light, and has never been directly observed. Because while the Sun gives us light, dark matter shapes the cosmos itself. Chapter 23. Dark matter is invisible, but it holds galaxies together. When you look up at the night sky, what you see is only a tiny fraction of what's really there. The stars, the planets, the nebulae and galaxies, all of it shines, all of it glows, all of it emits or reflects light. That's the universe as we know it. Or rather, it's the universe as we see it. But most of the universe does not shine, it does not glow, it does not reflect or absorb light in any way. In fact, most of the universe is invisible. It's made of something we call dark matter. Not because it's dark like shadows or empty space, but because it doesn't interact with light at all. It's not black. It's not dim. It's completely undetectable by electromagnetic radiation. It's invisible to every telescope, radio dish, and satellite we've ever built. And yet, it's real. We know this not because we can see dark matter, but because we can see what it does. Dark matter was first proposed to explain a strange observation. In the 1930s, astronomer Fritz Zwicky studied galaxies within a distant cluster known as the Coma cluster. He found that the galaxies were moving much faster than they should have been, based on the mass of the visible star. According to Newton's laws, they should have flown apart, but they didn't. Something was holding them together. That something was dark matter. Later, in the 1970s, astronomer Vera Rubin measured the rotation curves of spiral galaxies. She expected the stars near the center to rotate faster than those on the outskirts, just as planets orbit faster closer to the Sun. But what she found defied that logic. The outer stars were moving just as fast, sometimes even faster than inner ones. This didn't make sense unless something unseen was adding mass throughout the galaxy. And so the idea solidified. There was a form of matter, massive, gravitational, yet invisible, spread throughout space, not clustered like stars, but distributed in giant halos around galaxies. This dark matter provided the gravitational glue needed to keep galaxies intact, despite their speed of rotation. It became clear that dark matter wasn't just present, it was dominant. Today, the standard cosmological model tells us that normal matter, the stuff we're made of, atoms, molecules, planets, stars, makes up only about 5% of the total energy content of the universe. Dark matter makes up roughly the remaining 68% is something even more mysterious, dark energy, which we'll explore in the next chapter. But back to dark matter. What is it really? That remains an open question. We know what dark matter does, but we don't know what it is. It does not emit, absorb, or reflect light. It does not clump like ordinary matter. It doesn't interact with itself or with atoms in the ways we might expect. But it has mass and gravity. It bends space-time. It holds galaxies together. It shapes the large-scale structure of the universe. We've tried to detect it directly, with underground detectors buried deep beneath Earth's surface, shielded from radiation, hoping to catch even a single collision between a dark matter particle and a normal atom. So far, those efforts have returned no conclusive result. We've tried to produce it in particle accelerators, smashing protons together at near light speeds, in hopes that dark matter might appear as missing energy or unaccounted momentum. Again, nothing yet. There are theories, many of them. Some suggest dark matter is made of WIMPs, weakly interacting massive particles that barely touch the normal world. Others propose axions, incredibly light and elusive particles predicted by extensions of quantum theory. Some models even explore the possibility of entire dark sectors, mirror versions of our own particles and forces, hidden from sight. And yet, dark matter remains elusive. It's there in every simulation of galaxy formation. Without it, the structures we observe, galaxies, clusters, filaments, stretching across the universe, wouldn't exist. Normal matter alone cannot explain what we see. Even gravitational lensing, the bending of light around massive objects, reveals the presence of dark matter. When we observe light from distant galaxies being distorted by invisible masses along the way, we can map the contours of dark matter halos, tracing shapes we can't see, but know must be there. In this way, dark matter has become not just a placeholder, but a scaffolding, an invisible framework around which the luminous universe is built. Galaxies formed within its gravitational wells, stars ignited where it gathered. The visible universe is just a luminous dusting atop a far more massive, unseen foundation. And yet, despite all this knowledge, or perhaps because of it, dark matter remains one of the most profound puzzles in physics. If it's a particle, why can't we detect it? If it's not a particle, what is it? Could gravity itself behave differently on large scales? Some theories propose modified gravity, adjustments to Einstein's equations that might eliminate the need for dark matter altogether. But so far, none of these alternatives fully account for all the data. The case for dark matter, while indirect, remains incredibly strong. And so, the search continues. Every year, new detectors come online, new telescopes survey the sky, new maps are drawn, not of stars or galaxies, but of mass itself, inferred through its effects on everything it touches. And while we wait for a direct detection, we are learning more about where dark matter is, how it behaves, and how it shaped the cosmos we know. When you look at a spiral galaxy, remember, the beautiful swirl you see is just a trace. The real mass lies in a vast, unseen halo that extends far beyond the visible arms. It is quiet, cold, untouchable, but it is there, and it holds everything together. In the next chapter, we'll look at something even more baffling. A force, not of attraction, but of repulsion. A mysterious energy that pushes the universe apart faster and faster. Because if dark matter holds galaxies together, dark energy may be tearing the cosmos apart. Chapter 24, Dark Energy is Real, and it's accelerating the universe's expansion. When you imagine gravity, you probably think of it as a pull, a force that draws objects together. It keeps your feet on the ground, holds the moon in orbit around Earth, and binds galaxies into graceful spirals. Gravity is familiar. It is the reason why planets revolve around stars and why stars cluster into galaxies. But there's another force in the universe, one that does not pull but pushes, one that doesn't bind things together but drives them apart. It is called dark energy, and it makes up most of the universe. Unlike dark matter, which holds galaxies together with invisible mass, dark energy appears to be a property of space itself, a kind of built-in energy that increases as the universe expands. And instead of slowing things down, it speeds them up. This is not just speculation. In the late 1990s, two independent teams of astronomers set out to measure the rate at which the universe's expansion was slowing. They expected to find a gentle deceleration as gravity gradually pulled galaxies back from the momentum of the Big Bang. But what they found stunned the scientific world. The universe wasn't slowing down, it was speeding up. The expansion wasn't just continuing, it was accelerating. Galaxies weren't drifting gently apart. They were rushing away from each other at faster and faster rates. Something was counteracting gravity. Something was pushing. This repulsive effect could not be explained by any known matter or radiation. It was not tied to particles or fields we could observe. And so, the name dark energy was given, not because the energy itself is dark, but because its nature is unknown. But its effects are real, and they are vast. Today, dark energy is estimated to make up about 68% of the total energy content of the universe. More than 2/3 of everything, not stars, not gas, not dust, not planets, but this invisible, repulsive energy that fills space and causes expansion to accelerate. What is it? One possibility is that dark energy is the cosmological constant, a term Albert Einstein added to his equations of general relativity to maintain a static universe. After Hubble discovered expansion, Einstein abandoned the idea, calling it his biggest blunder. But the modern version of the cosmological constant has made a comeback. In this view, empty space has energy, not because it contains particles, but because space itself has structure, a baseline energy level. This constant energy density would not diminish as space expands. Instead, it would remain steady, and as more space is created, more energy appears with it. This might sound paradoxical, but in the framework of general relativity, it is mathematically sound. Another idea is that dark energy is not constant, but dynamic, driven by a field, sometimes called quintessence, that changes over time. In this view, dark energy may have had different effects in the past, and may evolve in the future. There are even more speculative theories that dark energy arises from interactions with hidden dimensions or from vacuum fluctuations predicted by quantum field theory. But so far we don't know. What we do know is this: the expansion of the universe is not slowing, it is growing fast, and over time, this acceleration changes the fate of the cosmos. In the distant future, trillions of years from now, galaxies beyond our local group will recede beyond the cosmic horizon. Their light will no longer reach us. Eventually, even the closest galaxies will become invisible. The universe will appear increasingly empty, increasingly dark. This is not the death of matter or the collapse of stars. Those changes take longer, but the structure of the universe, the connected web of galaxies and filaments, will gradually stretch apart, and the energy that fuels this separation will continue to act silently, without friction, without resistance. And even now, it's happening. Every second, space expands. Not because galaxies are flying through it like bullets, but because space itself is growing. Between galaxies, between clusters, across the great stretches of nothingness that connect the luminous islands of stars. And with that expansion comes more dark energy, because it is tied to space. It doesn't dilute like matter or fade like radiation. It persists, constant, or perhaps not constant, but evolving in a way we do not yet understand. Our current instruments are designed to measure this expansion. Telescopes like Euclid and the upcoming Nancy Grace Roman Space Telescope are being built to map the universe in fine detail, to trace how galaxies formed, how structure grew, and how dark energy behaved at different stages in cosmic history. We are not just observing galaxies, we are trying to read the story of acceleration, and it's written across billions of light years. Some cosmologists wonder if dark energy will grow so dominant that it eventually tears even bound structures apart, a scenario called the Big Rip. In this hypothetical future, galaxies are torn from clusters, stars from galaxies, planets from stars, atoms from molecules. Eventually, even space and time unravel. But this is speculation, a boundary of what physics allows, not what it predicts. For now, all we know is this: there is a force in the universe that acts not through contact, not through particles, but through geometry. And it dominates everything. It governs the future. It shaped the past. And it continues to push outward, always outward. Even as you rest now, space itself is stretching, not in some distant galaxy, but between every corner of the cosmos. Dark energy is not noise, it is silence, a pressure that speaks not in flashes or waves, but in the long unfolding of time. In the next and final chapter, we'll step back one more time. We'll ask the question that all of these discoveries raise: why is there something instead of nothing? Chapter 25. Why is there something instead of nothing? At the edge of every question in science, there is always one more. Every discovery leads to a new mystery. Every explanation uncovers something else waiting to be understood. We can describe stars, chart galaxies, model atoms, and track the expansion of the universe. But behind all of it, quietly, patiently, one question lingers. Why is there anything at all? Why is there something instead of nothing? It is a question that doesn't begin with data, or observation, or measurement. It begins with noticing, with recognizing that things exist, that there is a universe, that there is space, time, energy, matter, and minds, like yours, aware of it all. It would have been simpler, perhaps, for there to be nothing. No stars, no gravity, no atoms, no light, just absolute emptiness. Not a vacuum, but true nothingness. Not even the concept of space. And yet here we are. Something exists. And it is this something that science has spent generations trying to understand. The story begins with the Big Bang, the event or transition or condition that marked the beginning of our universe. We have a good picture of what happened after that moment, the expansion, the cooling, the formation of matter. But what came before? What set it in motion? Why was there a Big Bang at all? That remains unknown. Some model suggests the universe emerged from a quantum fluctuation, a brief imbalance in an underlying quantum field, where particles and antiparticles blink in and out of existence. According to this view, the vacuum itself is never truly empty. It seethes with energy, with potential, and under the right conditions, a fluctuation can become permanent, giving birth to a bubble of space-time that inflates into a universe. That bubble could be ours. Other models suggest our universe is just one region in a multiverse, a vast sea of universes, each with its own laws, its own constants, its own beginning. Some bubble into being and fade away. Others expand and evolve. If this is true, then our universe may not be special. It may be one of countless others, most of them lifeless, most of them without structure. In such a landscape, the question becomes not why is there something, but why does this something allow life? Why do the laws of physics in our universe permit atoms, stars, and consciousness? This line of thinking leads to the anthropic principle, the idea that we observe this universe because we are here to observe it. If the constants were different, we would not exist. And so, of course, we find ourselves in a universe where conditions permit existence. This doesn't explain the cause, but it may narrow the possibilities. Other explanations are more philosophical. Perhaps nothingness is unstable, not a default state, but a condition that cannot persist. Perhaps the laws of logic, mathematics, or probability favor existence over emptiness. Or perhaps the very question is flawed. Perhaps existence is not something that must be justified, but something that simply is. Still, the mystery remains. Every scientific law we know operates within existence. Gravity, electromagnetism, relativity, quantum mechanics, all describe how things behave once they are already here. But they do not explain why there is something to begin with. And yet, this question isn't just about physics. It reaches into every part of our experience. It touches on time, why it flows, why there is a past and a future. It touches on consciousness, why the universe not only exists, but knows that it exists. It touches on meaning, whether existence has a direction or a reason, or whether it is simply an unfolding pattern without need for purpose. And while science may not yet provide a full answer, it continues to give us something just as powerful. It gives us the ability to ask the question clearly. It gives us the ability to measure, to test, to explore. It gives us the means to trace existence backward, not to nothingness, but to the edge of understanding, where questions are sharper than conclusions. And that is where you are now, at the quiet edge, in a universe that expands faster than light, held together by invisible matter, lit by fusion, stirred by gravity, shaped by the delicate balance of chance and law. You are made of atoms, formed in stars. Your body is composed of matter that billions of years ago was drifting in the void between galaxies. You are, in every way, a part of this something, not separate from the universe, but shaped by it. You think because molecules in your brain carry charges across tiny distances. You feel because energy follows patterns that evolution has written into biology. You sleep because you live, and you live because, for reasons still unknown, there is something, not nothing, something, a beginning, a pattern, a flame that still burns in the silence of space. The universe is not finished. It is not complete. It is still becoming. And as you drift into sleep, the expansion continues. New stars are born. New questions emerge. New moments begin.